Workbench in Eclipse. Now we are focusing on Workbench. The Workbench provides the user interface structure for Eclipse. The purpose of the Workbench is to facilitate the seamless integration of tools. These tools contribute to extension points defined by the Workbench. The Workbench is responsible for the presentation and coordination of the user interface. The tools metaphor is not specific to development tools but can apply equally well to arbitrary applications. Note that the Workbench is sometimes called the generic Workbench to distinguish it from its instantiation in the Eclipse IDE, where it is called the IDE Workbench. Unlike SWT and JFace, which are both general-purpose UI toolkits, the Workbench provides the UI personality of the Eclipse platform and supplies the structures in which tools interact with the user. Because of this central and defining role, the Workbench is synonymous with the Eclipse platform UI as a whole, and with the main window the user sees when the platform is running. The Workbench API is dependent on the SWT API and to a lesser extent on the JFace API. The Workbench implementation is built using both SWT and JFace. Java AWT and Swing are not used. Here you can see ownerships of views and editors. The Workbench contains one or more Workbench windows, each of which contains 0 or more Workbench pages. The Workbench window supplies the trim widgets, and the Workbench page supplies the window contents. In theory, the Workbench window can contain any number of pages, but in practice there is never more than one page in a window. Views and editors are owned by page. Through a view factory and editor manager respectively. Editor manager stores the list of editors and their shared resources, and view factory stores a reference counted list of views. The Workbench works in terms of editor references and view references, and in situations where the distinction between editors and views is not important, we will simply use the term part. The implementation of the part, typically an iEditor part or iView part, is created lazily when it is first needed. A part reference exists for every tab, but the implementation is only created the first time it becomes visible. The page owns a set of perspectives Perspectives contains a layout and information about what action sets to enable. Although perspectives appears to contain views and the editor area, they only own a layout. Page itself maintains a reference count for how many perspectives are using each view, and has complete ownership of the parts and editor area. Not shown in this figure are classes perspective helper and editor area helper. Workbench contains workbench windows. Workbench window contains workbench pages, and workbench page contain editor manager, a view factory, and perspectives. Editor manager contains editor references, and editor reference contain 0 or 1 iEditor part. View factory contains reference counts, and reference count is connected to view reference. View reference contains 0 or 1 iView part. Perspective is connected to reference count, and increments are passed from perspective to reference count. Here you can see workbench objects and what they look like. The workbench contains one or more workbench windows. Each of which contains 0 or more workbench pages. Workbench window supplies the trim widgets, and the workbench page supplies the window contents. In theory, a workbench window can contain any number of pages, but in practice, there is never more than one page in a window. View and editors are owned by the page through a view factory and editor manager respectively. Editor manager stores the list of editors and their shared resources, and view factory stores a reference counted list in a list of views. Workbench works in terms of editor references and view references, and in this art and in situations where the distinction between editors and views are not important, and we will simply use the term part. The implementation of the part, typically iEditor part or iView part, is created lazily when it is first needed. As shown in this figure, a part reference exists for every tab, but the implementation is only created the first time it becomes visible. The page owns a set of perspectives. Perspectives contains a layout and information about what action sets to enable. Although perspective appears to contain views and editor area, they only own a layout. Page itself contains a reference count for how many perspectives are using each view, and has complete ownership of the parts and editor area. Not shown in this here are the classes perspective helper and editor area helper. Now here you can see the workbench, some of the visual components that make up the workbench. The workbench provide an extensive set of classes and interfaces for building complex user interfaces. Fortunately, you don't need to understand all of them to do something simple. We will start looking at some concepts that are exposed in the workbench user interface and their corresponding structure under the covers. Workbench. We have been using the term workbench loosely to refer to that window that opens when you start the platform. Let's drill down a little and look at some of visual components that make up the workbench. For the rest of the discussion, when we use the term workbench, we will be referring to the workbench window. Workbench window. The workbench window is the top level window in a workbench. It is the frame that hold the menu bar, toolbar, status line, shortcut bar, and pages. In general, you don't need to program to the workbench window. You just want to know that it's there. Note, you can open multiple workbench windows. However, each workbench window is a self-contained world of editors and views. So we will just focus on single workbench window. From the user's point of view, the workbench window contains views and editors. There are a few other classes used to implement the workbench window. Page, inside the workbench window, you will find one page, iWorkbench page that in turn contains parts. Pages are an implementation mechanism for grouping parts. You typically don't need to program to the page, but you will see it in the context of programming and debugging. Perspectives. Perspectives provide an additional layer of organization inside the workbench page. A perspective defines an appropriate collection of views, their layout, and applicable actions for a given user task. Users can switch between perspectives as they move across tasks. From an implementation point of view, the user's active perspective controls which views are shown on the workbench page and their positions and sizes. Editors are not affected by a change in perspectives. Views and editors. Views and editors are where we move beyond implementation details into some common plugin programming. When you add the visual components to the workbench, you must decide whether you want to implement a view or an editor. How do you decide this? A view is typically used to navigate a hierarchy of information, open an editor, or display properties for the active editor. For example, Project Explorer view allows you to navigate to the workspace hierarchy. The properties and outline views show information about an object in an active editor. Any modification that can be made in a view, such as changing property value, are saved immediately. Editor. An editor is typically used to edit or browse a document or input object. Modification made in an editor follows an open save close model, much like an external file system editor. Platform text editor and Java editor are examples of Workbench editors. Here you can see a Workbench window, and here you can see the page, and here you can see the views and the here editor. So inside the workbench you can see page, menu bar, toolbar. So views and editor are inside the page. Now we are considering building your Vivo editor according to a common life cycle. Here you implement create part control method to create SWT widgets that represent your visual components. You must determine which widgets to use and allocate any related UI resources needed to display your view or editor. When your view or editor is given focus, you will receive a set focus notification that you can set the focus to the correct widget. When your view or editor is closed, you will given a dispose message to signify the view or editor being closed. At this point, the control allocate create part control have already been disposed for you, but you must dispose any graphic resources such as cursors, icons or fonts that you allocate for the view or editor. Throughout this life cycle events, throughout this life cycle, events will fire from containing Workbench page to notify interested parties about opening, activation, deactivation, and closing of views and editors. Seems simple. It can be. That's the beauty of Workbench views and editors. They are just widgets folders and can be as simple or complex as you need them to be. We saw the simplest of views earlier when we built a hello world view. Let's look at it and look at this code again. Notice that we didn't have implement the dispose method, since we didn't do anything but create a label in the create part control parent method, if we had allocated any UI resources such as images, fonts, we would have disposed of them here. Since we expect the view part class, we inherit the do nothing implementation of dispose. As an example, we can consider a workbench class. The workbench class represents the top of the Eclipse user interface. Its primary responsibility is the management of workbench windows, dialogues, wizards, and other workbench related windows. Note that any code that is run during the creation of a workbench instance should not require to access to the display. This class is in package org.eclipse.e4.ui.internal. As an example 2, setting workbench preferences lets you set up the workbench to suit your needs. Open the step 1. Open the workbench and click Tools, Preferences. The Preferences dialog appears. The step 2. Set the preferences you want to use for your workbench sessions and click OK to save changes and dismiss the dialog, or click Apply to apply changes only. Step 3. Optional. Click the Restore Default button to restore dialog settings for the currently displayed preferences to their default values. Your workbench preferences are set. As an example 3, we are considering package org.eclipse.e4.ui.workbench. Application programming interfaces describing Eclipse for handlers and the workbench. Now we are considering a quick tour of the workbench in extending the workbench. When you open your workbench on a set of projects, it looks something like this. The workbench is the cockpit for navigating all of the functionality provided by plugins. By using the workbench, we can navigate resources and we can view and edit content and properties of these resources. When you open your workbench on a set of project, it looks something like this. The workbench is just a framework that can present various visual parts. These parts fall into two major categories: views and editors. Editors allow the user to edit something in the workbench. Editors are document centric, much like a file system editor. Like file system editors, they follow an open save close file lifecycle. Unlike file system editors, they are tightly integrated into the workbench. Views provide information about some object that the user is working with in the workbench. Views often change their content as the user selects different objects in the workbench. Views often support editors by providing information about the content of the active editor. Views, the workbench provides several standard views that allow the user to navigate or view something of interest. For example, the Project Explorer lets the user navigate the workspace and select resources. Editors allow the user to open, edit, and save objects. The Workbench provides a standard editor for text resources. Additional editors such as Java code editors or HTML editors can be supplied by plugins. Now we are considering views and editors. Let's look at it. Look this code. Class view part, abstract based implementation of all Workbench views. This is in the package org.eclipse.ui.part. Views and editors are where we moved beyond implementation details into some common plugin programming. When you add the visual components to the Workbench, you must decide whether you want to implement a view or an editor. How do you decide this? A view is typically used to navigate a hierarchy of information, open an editor, or display properties for the active editor. For example, Project Explorer view allows you to navigate workspace hierarchy. The properties and outline view show information about an object in the active editor. Any modification that can be made in a view, such as a change in property value, are saved immediately. Editor is typically used to edit or browse document or input object. Modification made in an editor follows an open save close model, much like an external file system editor. Platform text editor and Java editor are examples of Workbench editors. In either case, you will be building your view or editor according to a common lifecycle. You implement a create part control method to create the SWT widgets that represent your visual component. You must determine which widgets to use and allocate any related UI resources needed to display your view or editor. When your view or editor is given the focus, you will receive a set focus notification so that you can set the focus to the correct widget. When the view or editor is closed, you will receive a dispose message to signify that the view or editor is being closed. At this point, the controls allocated in create part control have already been disposed for you, but you must dispose any graphical resources such as cursors, icons, or fonts that you allocated for the view or editor. Throughout this life cycle, events will fire from the containing Workbench page to notify interested parties about the opening, activation, deactivation, and closing of views and editors. Seems simple. It can be. That's the beauty of Workbench and views and editors. They are just widget holders that and can be as simple or complex as you need them to be. Here, notice that we didn't have to implement the dispose method since we didn't do anything but create a label in the create part control parent method. If we had allocated any UI resources such as images or fonts, we would have disposed them here. Since we extend the view part class, we inherit the do nothing implementation of dispose method. This set focus to my widget for a label. This doesn't make much sense, but for more complex sets of widgets, you would decide which one get the focus. Now we are considering org.eclipse.ui.views in basic Workbench extension point using commands. First, let's take a look at the declaration of the extension in the plugin.xml. Here the identifier eclipse.ui.views. This extension point is used to define additional views for the workbench. A view is a visual component within a workbench page. It is typically used to navigate hierarchy of information like the workspace, open an editor, or display properties for the active editor. User can make a view visible from the window, then show view menu, or close it from the view local title bar. A view is a workbench part that can navigate a hierarchy of information or display properties for an object. Only one instance of any given view is open in a workbench. When a user makes selections or other changes in a view, those changes are immediately reflected in the workbench. Views are often provided to support corresponding editor. For example, an outline view shows a structured view of information in an editor. A properties view shows the properties of an object that is currently being edited. At the extension point, org.eclipse.ui.views allows plugins to add views to the workbench. Plugins that contribute a view must register the view in their plugin.xml file and provide configuration information about the view, such as its implementation class. The category or group of views which it belongs, and the name icon that should be used to describe the view in menus and labels. The interface for views is defined in iViewPart, but plugins can choose to extend the viewPart class rather than implement an iViewPart from scratch. We implemented a minimal view extension in the here. Now we will look at one that is aware to other workbench views and responds to user navigation and selection changes in the workbench. First, let's take a look at the declaration of the extension in the plugin.xml. This looks pretty familiar. We will see that the new view info view is contributed to the workbench. The view ID name and category are specified as we seen before. When we show the info view, the view within a list, pops up the list pre-populated with some data. We will start with the familiar create part control method. As we show before, this is where the widgets are represented, a view created. We will ignore some of the code to get started. The view creates and stores a list viewer and sets the content and label providers. It also registers itself as a selection provider. Here you can see it's register itself as the view creates and it stores a list viewer here. And label providers. It also registers itself as a selection provider for this view. The concept of selection provider, label provider, and content provider come from the JFace viewers. It obtained the service from its iView site. Which contains the information about the view's context, such as its workbench window, its containing page, its local services, and its plugin. We have covered a lot of common workbench concept by studying this extension here. Now service will be providing our input. Register myself as a selection provider for this view. Now we are considering plugin definition in plugin class. The readme tool plugin is defined in the manifest.mt file. The plugin definition includes bundle name, bundle symbolic name, plugin ID, bundle version, and bundle vendor of the plugin. We saw the most of these parameters before in our we can see the parameters here. The contribution plugin also defines a specialized plugin class org.eclipse.ui.examples.contributions.activator. The require bundle element informs the platform of the contribution plugins dependencies. The Workbench UI plugins are listed as required plugins. Along with the various core and expression plugins. Now we are considering contributing preference page in preference pages. The readme tool uses this extension point to add the readme example preference page. Here the identify org.eclipse.ui.preference pages. The workbench provides one common dialog box for preferences. The purpose of this extension point is to allow plugins to add pages to the preference dialog box. When preference dialog box is opened, initiated with from the menu bar, pages contributed to this way will be added to the dialog box. The org.eclipse.ui.preference pages extension point allows you to contribute pages to the general preferences window preferences dialog. The preference dialog presents a hierarchical list of user preference entries. Each entry displays a corresponding preference page when it's selected. The readme tool uses this extension point to add the readme example preference page. This markup defines the preference page name readme example. Which is implemented by the class readme preference page. The class must implement the iWorkbench preference page interface. The Workbench uses core runtime preference mechanism to access all nodes in the preference tree and their corresponding pages. This list can be initialized from the information in the preferences services without running any plugin code. Now we are considering new Shift Alt N in file menu in workbench menus. Enables you to create new resources. Before you can create a new file, you must create a project in which to store the file. the undo in edit menu. This command reverses your most recent editing action. Go into in navigate menu. This command refocuses the active view so that the current selection is at the root. This allows web browser style navigation within hierarchies of artifacts. Open project in project menu. This command opens the currently selected project or projects. The selected project must currently be closed for this command to be available. New window in window menu. This command opens a new workbench window with the same perspective as the current perspective. Help contents in help menu. This command displays the help content in a help window or external browser. The help contents contains help books, topics and information related to the workbench and installed features. Now we are here we are considering exiting the workbench. To exit the workbench, select File, then Exit from the menu bar or close the workbench with the window close button X. Each time the workbench is exited, the workbench is automatically saved, including all open perspectives and windows. The next time the workbench is reopened, it will appear exactly as it was when it was last closed. To exit the workbench, select File, then Exit from the menu bar or close the workbench with the window close button X. When the latter option is used, a prompt will ask if you ready to wish to exit the workbench. Note, this dialog also presents an option to turn off the prompting. To turn it back on, open the Preferences dialog and choose the General, then Startup and Shutdown preference page. Check the Confirm Exit when closing last window checkbox. Now we are considering files in resources. Files comparable to files as you see them in the file system. Now we are considering a root in resource hierarchies, the top level of the workbench content in the file system. Now we are considering linked resources. The linked resource target path can be changed by selecting edit button in the file, then properties, then resource property page of the linked resource. Linked resources are files and folders that are stored in locations in the file system outside of the project location. These special resources can be used to add files and folders to your project that for some reason it must be stored in a certain place outside of your project. For example, a linked resource folder can be used to store built output separately from your resource file. You can even use linked resource to overlap the other resources in the workspace, so resources from one project can appear in another project. If you do want to have overlapping resources in your workspace, do so with caution. Keep in mind that this means changing a resource in one place will cause simultaneous changes in the duplicate resource. Deleting one duplicate resource will delete both. Deleting a linked resource will not cause the corresponding resource in the file system to be deleted. However, deleting child resources of linked folders will cause them to be removed from the file system. Linked resource target paths can be either defined as absolute path or relative to a path variable. The linked resource target path can be changed by selecting edit button in the file, then properties, then resources property page in the linked resource. A list of linked resources that exist in the project can be seen and edited from the file, then properties, then resource, then linked resource property page under the linked resource tab. Some plugins built on top of the Eclipse platform are not compatible with linked resources. If this is the case, you can completely disable the linked resource feature to prevent them from being created in your workspace. Linked resources can be disabled from the general, then workspace, then linked resources preferences page. Certain types of project or team repository providers may also disallow linked resources from being created in some projects. Now we are considering virtual folders. Virtual folders are folders that exist only in the Eclipse workspace tree and have no file system location. By using virtual folders, files and folders can be organized in a project hierarchy independently of the file system location of those resources. Regular file and folder resources cannot be created under virtual folder since they need the file system location as their parent in order to exist in the file system. Only other virtual folders or linked resources can be created directly under a virtual folder. Now we are considering path variables. Each project contains a predefined set of path variables available for defining linked resources, including Eclipse _home, parent _lock, project locked, and workspace lock. Path variables specify location on the file system. Location of linked resources may be specified relative to these path variables. They allow you to avoid reference to a fixed location on your file system. By using path variable, you can share projects containing linked resources with team members without requiring the exact same directory structure as on your file system. Path variables can be either defined at the project level or at the workspace level. Creating path variables at the project level ensures that projects that contain linked resources using those path variables remain portable across workspace and computers. Each project contains a predefined set of path variables available for defining linked resources, including Eclipse home, parent lock, project lock, and workspace lock. Now we are considering resource filters. Ensure resource filters can be created, edited, and removed in the file system. Removed in the file, then properties, then resource, then resources filters property page for a project or folder resource. Resource filters allow you to configure which files and folders are included automatically in a project resource hierarchy when refresh is performed. By adding resource filters to a project or folder, you can systematically prevent some file system entries to be displayed in the resource tree. A resource filter is either include only or exclude all type and can apply to either files, folders, or both. Resource filters only apply to files and or folders that are implicitly included in the workspace by the refresh operation. Link files and folders are not affected by resource filters since they need to be created explicitly by the user. The include resource filter allows only files or folders that match the filter condition to be included in the workspace during refresh operation. If multiple include filters exist, the element included will be those who match any of the existing include filters. The exclude resource filter prevent all files or folders that match the filter condition to be included in the workspace during refresh operation. If the multiple exclude filters exist, the element excluded will be those who match any of the existing exclude filters. If both exclude and include filters exist in the given folder or project, only files or folders that match any of the include filters and do not match any of the exclude filters will be included in the workspace. Resource filter can apply recursively to all children of the project or folder it is created in. In such case, the resource filter will apply to a subfolder as if it was created in that subfolder itself following the rules mentioned above. Resource filters can be created, edited, and removed in the file properties, resources, and then resource filters property page for a project or folder resource. Resource filters can also be created in a folder before that folder is created in the workspace by setting resource filters button in the advanced section of the new folder wizard. Now we are considering working sets. In order to modify the window working set, you need to enable the window working set command group via window, then perspective, then customize perspective. Working sets group elements for display in views or for operations on a set of elements. The navigation views use working sets to restrict the set of resources that are displayed. If a working set is selected in the navigator, only resources, children of resources, and parents of resources contained in the working set are shown. The problems view, task view, and bookmarks views can also be filtered based on the working set via the filters view menu item. When using the search facility, you can also use working sets to restrict the set of elements that are searched. Different views provide different ways to specify a working set. The views in the Eclipse SDK use window working set by default. The window working set is initially empty. In order to modify the window working set, you need to enable window working set command group via window, then perspective, then customize perspective. You can then modify the window working set via window, then working set menu, or via corresponding menu, corresponding toolbar button. Views that supports the working set use the working set selection dialog to manage existing working sets and to create new working sets. Now we are considering builds. You can configure your preferences, command, link general, then workspace to perform builds automatically on resource modification. A build is a process that derived new resources from the existing ones, updates the existing resources or both. In the workbench, different builders are invoked for different types of project. For example, when a build is triggered for a Java project, a Java builder converts each Java source file .java files into one or more executable class files .class files. Builders usually enforce the constraint of some domain. For example, a web link builder could update links to files whose name or location changes. There are two kinds of builds. An incremental build leverages a previously built state and applies the forms of the configured builders to the resources that have changed since the previous state was computed, that is, since the last build. The other one is a clean build, discard any problems and previously built state. The next build after a clean will transform all resources according to the domain rules of the configured builders. Incremental and clean builds can be done over a specific set of projects or workspace as a whole. Specific files and folders cannot be built. These are two ways that builds can be performed. Automatic builds are performed as a resource are saved. Automatic builds are always incremental and new operate over entire workspace. You can configure your preferences, general then workspace, to perform builds automatically on resource modification. The other way is manual builds. Manual builds are initiated when you explicitly select a menu item or press the equivalent shortcut key. Manual builds can be either clean or incremental and can operate over collections of projects or the entire workspace. Now we are considering local history. A local edit history of a file is maintained when you create or modify a file. A local each time you edit and save the file, a copy is saved so that you can replace the current file with the previous edit or even restore a deleted file. You can also compare the content of all the local edits. Each edit in the local history is uniquely represented by the date and the time of the file was saved. Only files have local history. Projects and folders do not. Sorry, it means only files have local history. Projects and folders do not. Now we are considering customize welcome dialog in customizing welcome in customizing the workbench. Option home page theme. This option will change the overall appearance of welcome. Default to circles. Now we are considering rearranging the main toolbar. You can rearrange sections of the main toolbar. Toolbar sections are divided by a thin vertical line. Step 1. Make sure the toolbar is unlocked. The toolbar is unlocked if it has thick vertical bars next to the thin vertical bar dividers. If it is locked, unlock the toolbar by right clicking the toolbar and selecting the lock the toolbar's menu item. Step 2. Grab the section of the toolbar you want to rearrange by moving the mouse over the thick vertical line on the left side of the desired segment. The mouse cursor change its shape to indicate that you can click to move the toolbar section. Click and hold the left mouse button and to grab the toolbar section. Move the step 3 and step 4. Move the section left and right or up and down and release the mouse button to place it to its new location. To prevent accidental changes to the toolbar, lock it again by right-clicking the toolbar and selecting Lock the Toolbar's menu item. Now we are considering changing the key bindings. Use command general then keys preference page to assign key sequences to many of the commands in Eclipse. The function of the keyboard can be extensively customized in Eclipse. Now we are considering changing fonts and colors to change these fonts here. By default, the Workbench uses fonts and colors provided by operating system. The Workbench lets you to directly configure the following fonts: banner fonts, dialog fonts, header fonts, text font, ignored resource font, outgoing change font, console font, detail plain text, memory view table font, Java editor text font, properties file editor text font, compare text font, Java compare text font, Java properties file compare text font, part tile font, view message font. To change these fonts, open the command, open the general, then appearance, then colors and fonts preference page. Select select the font you want to change. Then step 3, click edit, and step 4, use the dialog which opens the open to select a font. Step 5, click OK. Note you can also click use system font to set the font to a reasonable value chosen by the operating system. For example, on Windows, this will use the font selected in the display properties control panel. Plugins that use other fonts may also provide preference entries to allow them to be customized. For example, Java development tools provide a setting for controlling fonts used by the Java editor. See Java, then Java editor text font on the preference page. In addition to the above, some text is always displayed in the system font. For example, the navigator tree always does this. To change the font used in these areas, you can use the configuration tools provided by the operating system. For example, the display properties control panel on Windows, or the .xdefault file in Motif. Now we are considering controlling single and double click behavior. To do this, you can follow these steps. You can control how the Workbench responds to single and double clicks. To do this, open the general preference page, select the behavior you want to change from the open mode group, click OK. The effect of these selections varies by view. For example, in one of the navigation views, double click will cause a single click on a resource to select it, and a double click to open it in the editor. Single click will cause the single click on a resource to both select it and immediately open an editor on it. The checkboxes are under single click. Radio button further define the single click behavior. Checking select on hover will cause the resource to be selected if you hover over it with the mouse. Checking open when using arrow keys will cause the resources to be open if you use the arrow keys to navigate it. Now we are considering importing and exporting preferences. To import preference file, you can follow these steps. Preference files can be both imported to and exported from the Workbench, allowing you to easily share individual or group preferences. The import wizard can be used to import preferences from the file system to the Workbench. To import a preference file, select file, then import. Step 2, in the import wizard, select general, then preferences, and click next. Click browse and locate the preferences file on the file system. Click import all to accept all the preferences defined in the file. If you want to import only few preferences, choose them from the list, then click finish. The export wizard can be used to export preferences from the Workbench to the file system. To export the file, select file, then export. Step 2, in the export wizard, select general, then preferences, and then click next. In step 3, click export all to add all of the preferences to the file. Step 4, if you want to export only few preferences, choose them from the list. Step 5, click browse and locate the preferences file on the file system. Step 6, click finish. Note, if no changes have been made to the original preferences settings, the preferences file will be empty. Now we are considering large file associations per product customization. Example product customization file contents to specify large file associations. The product customization file can be specified via command line parameter, plugin customization, path to file. Example product customization file contents to specify large file associations. All type with the preference needed by the preferences page UI. Default show prompt for all types that don't have preference. Specify edit associations per type and file size. Now we are considering Workbench toolbar. Here is an example of the toolbar in resource perspectives. Now we are considering performing a TCL search from the Workbench. In searching the Workbench in TCL or TCL development. Step 1, copy the contents of the http.tcl from the http 1.0 standard package and paste it to the new TCL file in an exemplary project. Step 2, in the TCL perspective, click search button in the Workbench toolbar, or use TCL use search then TCL from the menu bar. If it is not already selected, select the TCL search tab. In the search string field, type http_config. In the search for area, select method, and in the limit to area, select declaration. Verify that the scope is set to the workspace. Then click search. While searching, you may click cancel at any time to stop the search. Partial results will be shown. And step 5, in the TCL perspective, the search view shows the search results, and the first match is highlighted in the editor. Search results view, you may the show next match, and show previous match buttons to navigate each match. In this example here, the single match. Note that if the file in which a match was found is not currently open, it is opened in an editor when you select the match in the search view. Step 6, when you navigate to a search match using the search view buttons, the file opens in the editor at the position of the match. Search matches are triggered with the search marker in the vertical ruler as on the screenshot. It's not shown here at the moment. Now we are considering performing a Java search from the Workbench in searching the Workbench. Step 1, in the Java perspective, click the search button in the Workbench toolbar, or use search then Java from the menu bar. If it is not already selected, select Java search tab. Step 3, in the search string field, type run test. In the search search for area, select method, and in the limit to area, select references. Verify that the scope is set to workspace, then click search. While searching, you may click cancel at any time to stop search. Partial results will be shown. Step 4 in the Java perspective, the search view shows the search results. Use the show next match and show previous match buttons to navigate to each match. If the file in which the match was found is not currently open, it is open in an editor. When you step 5, when you navigate to a search match using search view buttons, the file opens in the editor at the position of the match. The search matches are tagged with the search marker in the rulers. Now we are considering Workbench menu contributions in advanced Workbench concepts. The extension point name menus. The command this location of actions. The commands can be placed in the main menu and toolbar. Command can be placed in part context menus as well as view menus and view toolbars. The placement is controlled by the location URI, and the visibility is controlled by the visible when co-expression. The details. The extension point should be used to place commands in menus and toolbars so they can be executed by the user. Now we are considering undo and in the IDE Workbench in undoable operations. This model-based registration allows plugins that manipulate the workspace to obtain the appropriate undo context, even if they are headless and do not reference any Workbench classes. The interface undo context, and undo context is used to tag operations as being applicable to certain context. The undo context is used to filter the history of operations available for undo and or redo, so that only operations appropriate for a given undo context are shown when the application is presenting that context. The interface iOperation history. iOperation history tracks a history of operations that can be undone or redone. Operations are added to the history once they have been initially executed. Clients may choose whether to have the operations history perform initial execution or to simply add an already executed operation to the history. These are in the package org.eclipse.co.commands.operations. We have The notion of the workbench wide undo context is fairly general. It is up to the workbench application to determine what specific scope is implied by the workbench undo context, in which views and or editors use the workbench context when providing undo support. In the case of Eclipse IDE workbench, the workbench undo context should be assigned to any operation that affects the IDE workspace at large. This context is used by the views that manipulate the workspace, such as a resource navigator. The IDE workbench install an adapter to the workspace for undo context that returns the workbench undo context. This model-based registration allows plugins that manipulates the workspace to obtain the appropriate undo context, even if they are headless and do not reference any workbench classes. Other plugins are encouraged to use these techniques for registering model-based undo context. Undoable operations are provided by IDE plugin that allows you to execute undo or redo common workspace manipulations. Operations are provided for creating, moving, copying, and deleting projects, folders, and files. IDE plugins uses these operations to provide undo support in the resource navigator. The classes that also be used by client, they are available in the package org.eclipse.ui.ide.undo. Using the workspace undoable operations is similar to the example shown for using undoable operations here. The primary difference is that the sum of the details, such as assigning the appropriate undo context, are handled internally by the operation. The following snippet here shows how to use an undoable operation for creating a new file. The operation is here. The operation is configured with the file handle for the file to be created and input string with the initial context. And the label describing the operation. Internally, the operation will assign the workspace undo context and handle other details such as keeping track of the resources. The operation manipulates. To execute the operation, caller used the standard operation history protocol. Note that the caller is responsible for providing the progress monitor if desired. And the adaptable that can provide the shell that should be used for any prompting. The utility class workspace undo util provides a utility method for creating necessary adapter from the shell. Callers are also responsible for determining whether to execute the operations in the UI thread, the background, or a workbench job. If the operation should be executed in the background, then the caller should create the appropriate progress monitor and run the snippet shown here, appropriate runnable. The undo and redo of the operation will be performed by the undo and redo action handlers when the user initiate undo or redo. The standard workbench action handles use advanced undoable operation tool protocol to determine how to perform the undo and redo operations. All of the workspace operations implement protocol that instruct client to run the undo or redo of the operation in the background if possible. Get the operation history, obtain the appropriate undo context for my model, create an operation and assign its context. Handle exceptions here. Now we are considering org.eclipse.ui perspectives in perspectives. The following markup is used by the Workbench in defining its own resource perspective. The identifier org.eclipse.ui.perspectives perspective perspectives. This extension point is used to add perspective factories to the Workbench. A perspective factory is used to define initial layout and visible action sets for the perspective. The user can select perspective by invoking open perspective submenu of the window menu. The platform itself defines the one perspective, the resource perspective. Other platform plugins such as help system and the Java tooling define additional perspectives. Your plugin can define its own perspective by contributing to the org.eclipse.ui.perspectives extension point. The specification of the perspective in the plugin.xml is straightforward. The following markup used by the Workbench by defining its own resource perspective. A plugin must supply ID and name for the perspective along with the name of the class that implements the perspective. An icon can also be specified. The perspective class should implement iPerspective factory. Now we are considering decorators. This decorator is contributed by PDE using the org.eclipse.ui.decorators extension point. The identifier org.eclipse.ui.decorators. This extension point is used to add decorators to views that subscribes to the decorator manager. As of 2.1, there is the concept of a lightweight decorator that will handle the image managed for the concept of the lightweight decorator that handle the image management for the decorator. It is also possible to declare a lightweight decorator that simply overlays an icon. When enabled, that requires no implementation from the plugin. Your plugin can use decorators to annotate the images for the resources and other objects that appear in the Workbench views. Decorators are useful when you plug when your plugin adds functionality for existing resource types, many of the standard Workbench views participate in showing decorations. For example, PDE contributes decorators that allow you to distinguish between binary and source projects. The com.example.helloworld project is the only source project shown in the project explorer. Note how all of the other binary projects show the binary decorator at the top of the left of the project icon. This decorator is contributed by PDE using org.eclipse.ui.decorators extension point. There are several different ways to supply a decorator implementations. The markup uses the simplest way, known as the declarative lightweight decorator. When the declarative lightweight decorator is defined, the markup contains a complete description of the decorator's icon, placement, and enabling conditions. Declarative decorators are useful when only an icon is used to decorate the label. The plugin needed only to specify a quadrant where the decorator should be overlaid on the regular icon and the icon for the overlay. As shown in the picture, the PDE binary icon is overlaid in the top left quadrant of the package icon. If your plugin needs to manipulate label text in addition to the icon, or if the type of the icon is determined dynamically, you can use the non-declarative lightweight decorator. In this case, an implementation class that implements lightweight label decorator must be defined. The designator class is responsible for supplying a prefix, suffix, and overlay image at runtime, which are applied to the label. The mechanics of concatenating the prefix and suffix with the label text and performing overlay are handled by the Workbench code in the background thread. Thus, any work performed by your plugin is lightweight label decorator implementation must be UI thread safe. Now we are considering key bindings in Workbench key bindings. Plugins can define key bindings along with the commands in the org.eclipse.ui.binding extension point. The identifier org.eclipse.ui.bindings, the org.eclipse.ui.bindings extension point is used to declare bindings and schemas. Schemas are a set of one or more bindings, and a binding is a mapping between certain groups of conditions, some user input and a triggered command. Here the extension pointed code is not shown here. The association between the command and the key combinations that should invoke the command is called key binding. Plugins can define key bindings along with the commands in the org.eclipse.ui.bindings extension point. There is our friend org.eclipse.ui.file.save. In Eclipse, the Workbench registers the save action as a handler for this command ID in every Workbench window. The sequence attributes for the key binding defines the key combination that is used to invoke the command. When Workbench save action is active, the key combination Ctrl+S will invoke it, since the Workbench uses the same command ID for the save action. Now we are considering element factories. In element factories, when the following code snippet is from the workbench plugin.xml. The identifier org.eclipse.ui.element factories. This extension point is used to add elements factories to the workbench. An element factory is used to recreate IAdaptable objects which are persisted during Workbench shutdown. When the Workbench is shut down, shown by the user, it must save the current state of the IAdaptable object that are shown in the Workbench. An object state is stored in by the saving the primitive data parameters of the object in a special format and memento. The ID of the factory that can recreate the object from the memento is also stored, and the data is saved in the file system. When a platform is restarted, the Workbench finds its element factory associated with imemento's factory ID. It finds the factory by checking the plugin in the registry for the contribution to the org.eclipse.ui.element factories extension. The markup is pretty simple. We just have to specify the ID of the factory and the corresponding class that implements the factory. The following code snippet is from the Workbench plugin.xml. Now we are considering considering SWT and accessibility in accessible user interfaces. The SWT implements an interface, accessible listener, which provides basic accessibility information such as description of controls, help text, and keyboard shortcuts to clients. The interface accessible listener classes that implement this interface provide methods that deal with the events that are generated when an accessibility content sends a message to the control. This is in the package org.eclipse.accessibility. Because of SWT uses the operating system's native widgets, user interface built with SWT will inherit any assistive technologies that has been installed on the host operating system. SWT implements an interface accessible listener which provide basic accessibility information such as description of controls, help text, and keyboard shortcuts to clients. If you are developing assistive technologies that need more information or want to improve upon the basic accessibility of the Workbench, you can add your own listeners and override the default accessibility behavior in the platform. See the package org.eclipse.swt.accessibility for more detail. Now we are considering single click in SWT controls. In this way, you are shielded from knowledge that which widgets event triggered the open event. The class open strategy implementation of single click and double click strategies. This is in the package org.eclipse.jface.util. In the general preferences, allow user to specify whether view should open their object on single or double click. The JFace provides a utility class open strategy to handle the logistics of single and double click at the SWT control level. The open strategy is configured by the general preferences dialog so that it honors the current Workbench open preferences. In fact, the JFace viewers use this class to implement the open listener. You must create open strategy for and associate with it with your SWT control. The open strategy will hook the appropriate events and interpret them based on your preferences. Your job is to add an open listener to the strategy that implements the code for open. In this way, you are shielded from knowledge about which widgets event triggered for open event. The other Workbench preferences for open select on hover open using arrow keys are also handled by open strategy. If you use JFace viewer, so open strategy class to implement this means that the right thing will happen if you use JFace viewer, so open strategy class to implement open behavior. Code to handle the open event. Now we are considering working sets. You can obtain an iWorking set iWorking set manager using iWorkbench API. The interface iWorking set manager. A working set manager stores working sets and provide property change notification when a working set is added or removed. This is in the package org.eclipse.ui. Users often find it necessary to filter views such as navigator view in order to reduce clutter. Plugins can assist in filtering using different techniques. Resource filters can be used to filter by file name. Plugins contribute resource filters that the user can enable using a viewer's filter selection dialog. Working sets can be used to filter resources by only including specified resources. Working sets are selected using the views working set dialog. If your plugin implements a view that shows resources or objects that are adaptable to iResource, you should support working sets. iWorking Set Manager provides API for manipulating working sets. You can obtain an iWorking Set Manager using iWorkbench API. iWorking Set Manager allows you to manipulate and create working sets. Create working set selection dialog returns a working set dialog that shows the user's current working set. You can get the selected working set from the dialog once it is closed. Create working set edit wizard returns a working set edit wizard for editing the specified working set. Get working set method returns a list of all defined working sets. Get working set string name method returns a working set specified by the name. iWorking Set Manager also provide property change notification as working sets are added, removed, or as they change. If your view or editor needs to respond to changes in the selected working set, it can add a listener for change _ working _ set _ content _ change. Now we are considering defining activities in filtering large user interfaces. Let's look at the first at a simplified version of how Eclipse SDK plugin defines two conventional activities, one for developing Java software and one for developing plugins. Activities are defined using here you can see the identifier org.eclipse.ui.activities. The org.eclipse.ui.activities extension point is used to declare activities and associated elements. Activities are used by the platform to filter certain plugin contributions from the user's view until such a time they express interest in them. This allows Eclipse to grow dynamically based on the usage pattern of a user. Activities are defined using org.eclipse.ui.activities extension point. Let's look at the first simplified version of how the Eclipse SDK plugin defines the two conventional activities, one for developing Java software and one for developing plugins. Activities are assigned a name and a description. Name and the description can be shown to the user whenever they are enabling and disabling conventional activities, or otherwise shown information about the activity. The ID of the activity is used when defining patterns, bindings, or other relationships between activities. Now we are considering progress service in Workbench concurrency support. The method void busy cursor while I runnable with progress runnable. Set the cursor to busy and run the runnable in a non-UI thread. Calling thread will be blocked for the duration of the execution of the supplied runnable. After the cursor has been running for a For get long operation time, replace with the progress monitor dialog so that the user may cancel. Do not open the progress monitor dialog if there is already a model dialog open. Interface iProgress service. The progress service is the primary interface to the Workbench progress support. It can be obtained from the Workbench and then used to show progress for both background operations and operations that run in the UI thread. This is in the package org.eclipse.ui.progress. The Workbench progress service, iProgress service, is the primary interface to the Workbench progress support. It can be obtained from the Workbench and then used to show progress for both background operations and operations that run in the UI thread. The main purpose of this class is to provide one-step shopping for running operations, removing need for plugin developers to decide what mechanism should be used for showing progress in a given situation. Another advantage is that the progress dialog shown with these methods provide the good support for indicating when an operation is blocked by another and give the user control to resolve the conflict. Where possible, long-running operation should be run using iProgress service busy cursor while. This method will initially put up busy cursor and replace it with the progress dialog if the operation lasts longer than the specified time threshold. The advantage of this method over using a progress dialog is that the progress dialog won't be shown if the operation is short running. If your operation must update the UI, you can always use display.async exec or display.async exec to run the code that modifies the UI. None UI work. Now we are considering contributing a property page in Workbench resource support. The README tool contributes two property pages. Identifier org.eclipse.ui.property pages. This extension point is used to add additional property page for objects of a given type. Once defined, use property pages will these property pages will appear in the properties dialog for object of that type. You can contribute a property page for an object using the org.eclipse.ui.property pages extension point. An object property page is invoked using properties menu in any view that shows the object, such as resource navigator view. This menu is available when a single object is selected. README tool contributes two property pages. When you define a property page, you specify object class for which this page is valid. Objects of this class will include your page when the properties are shown. You may optionally supply a name filter that further refines the class. In the README tool example, the both pages are contributed for objects of type ifile with the .readme file extension. Property pages are not limited to Workbench resources. All objects showing up in the Workbench, even domain-specific objects created by other plugins, may have property pages. Any plugin may register property pages for any object type. Property pages look a lot like preference pages, except there is no hierarchy or categorization of property pages. In the dialog box, both the readme property pages appear in the main list of pages. Now we are considering logging with the use of the default login mechanism in status handlers in status handling. This code is the example of addlog status property page. The class status adapter. The status adapter wraps an instance of status subclass and can hold additional information either by using properties or by adding new adapter used during status handling process. This is the package org.eclipse.ui.status-handlers. In order to log extra information with the use of the default logging mechanism, it is necessary to perform some additional steps. The status manager provides you with an API that allows you to hook into the mechanism. And this code example add logger status status proper use. Now we are considering services. For example, here the interface iHandler service provides service related to activating and deactivating handlers within the workbench. This is in the package org.eclipse.ui.handlers. The workbench defines number of services that can be retrieved from org.eclipse.ui.services.iService locator. Services provide a way for components to retrieve information about the workbench without always having to go to the global singleton platform UI.get workbench. For example, here some services provide two optional abilities which are usually specified in the services interface Java doc. Services that support listeners can clean up the listeners automatically when the component org.eclipse.ui.services.iService locator used to get the service is disposed. And other optional abilities, services can provide more localized services depending on which component they are requested from. Now we are considering Docker bow in drop cursors in workbench window layout. Here Docker bow here, the view will appear above the view underneath the cursor. Now we are considering editing files outside the workbench in working with other editors. The same external editor can also be used by launching it outside of the workbench. External editor can be launched by on a .ini file by double clicking on it in the project explorer. The same external editor can also be used by the launching it outside the Workbench. Step 1, close any editors that are open on the .ini file. Step 2, in the File System Explorer, navigate to the directory where the Workbench was installed and go to the Workspace subdirectory. Step 3, edit the .ini file and save it. Do not use the Workbench Project Explorer to open the editor. Step 4, return to the Workbench and in the Project Explorer view, select your project. Step 5, choose the refresh from the project's context menu. This instructs the Workbench to look for any changes to the projects that have been made in the local file system by external tools. Step 6, select the .ini file. Step 7, for the little variety, choose open with, then choose open with, then text editor from the file's pop-up menu. Step 8, observe that the Workbench own default text editor is opened. In the default text editor, verify that the externally made changes are reflected in the Workbench. The Workbench stores all of its resources in the local file system. This means the System File Explorer can be used to copy files from the Workbench workspace area even when the Workbench is not running. Resources can also be copied to the workspace directly. Use refresh to update the Workbench with any changes made outside the Workbench. Now we are considering org.eclipse.ui.new wizards in Workbench wizard extension points in dialogues and wizards. The readme tool example uses this extension point point definition to add readme file wizard. The identifier org.eclipse.ui.new wizards. This extension point is used to register resource creation wizard extensions. Creation wizards appear as choices with the new dialog and are typically used to create folders and files. You can add a wizard to the file new menu options in the Workbench using the org.eclipse.ui.new wizard extension point. Readme tool example uses this extension point definition to add the readme file wizard. The category describes the grouping for the wizard. An optional parent category establishes the new category as a child of an existing category. Top level categories will appear in the file new menu. In this example, the parent category is set to an example category. Where did the parent category where did the parent category come from? The org.eclipse.ui plugin defines the standard example category in this markup here. This category appears in the file new menu. The readme tools category name defines the label that is used for next layer of grouping underneath the parent category. These categories are shown as the second level in the tree shown in the new example wizard. Wizard's name and an icon are shown underneath when you expand the category. The description of the selected wizard is shown at the top of the wizard when you select it. This information about the wizard appears solely because of the markup of the plugin.xml. None of the plugin code runs until the cursor and the user chooses to the next button. Once this happens, the workbench will instantiate the wizard class specified in the markup and pass it to the expected selection class. This class identified in this extension, readme creation wizard, must implement iNew wizard interface. Most wizards do so by extending the platform wizard class through this. Although this is an implementation mechanism and not required by the extension point, the wizard itself does little but create pages inside it. Let's now we are considering org.eclipse.ui.import wizards. The wizards appear uncategorized in wizard dialog. The identifier org.eclipse.ui.import wizards, this extension point is used to register import wizard extensions. Import wizard appear as choices within the import dialog and are used to import resources into the workbench. You can add the wizard to the file, then import menu option in the workbench using org.eclipse.ui.import wizard extension point. The process for defining the extension and implementing the wizard is similar to org.eclipse.ui.new wizards. The primary difference is the markup is that import wizard do not define or assign categories for the wizards themselves. Wizards appear uncategorized in wizard dialog. The wizard supplied in the class parameter for the markup must implement iImport wizard. Its pages are typically extended from wizard import page. Now we are considering org.eclipse.ui.export wizards. The wizards appear uncategorized in the wizard dialog. The identifier org.eclipse.ui.export wizards. This extension point is used to register export wizards extensions. Export wizards appear as choices within the export dialog and are used to export resources from the workbench. You can add a wizard to the file, then export menu option in the workbench using the org.eclipse.ui.export wizards extension point. The process for defining the extension and implement the wizard is similar to org.eclipse.ui.new wizards. The primary difference is the markup is that export wizards do not define or assign categories for wizards themselves. The wizards appear uncategorized in a wizard dialog. The wizard supplied in the class parameter of the markup must implement iExport wizard. Its pages are typically extended from wizard export page. Now we are considering properties view in Workbench integration with web editors in creating web applications. The properties view window, then show view, then properties contains a list of attributes and editable attributes values. For example, when you select an image tag img, width and height values appear for editing. In addition, any other attributes allowed by the standard specified in the doc type for the file, such as the HTML 4.0, 4.0.1 DTD, are listed. When you click the value column of the property, you can select from among the list of available attribute values. The pop-up menu in the properties view enables you to undo, cut, copy, paste, delete, and select all. The options that are available at a given time depends on where the cursor is located. When you right click to display the pop-up menu, to see the pop-up menu that contains undo, cut, and so on, the property value field must be active. This is accomplished by selecting the property and then selecting its value. Otherwise, the pop-up menu will contain different options. Use the restore default value button to change any value back to the default setting. After you are in the properties view, you can modify the property values for specific tags. To edit another tag using properties view, move the cursor within the editing area of the source page or design page to the tag where you want to edit. The appropriate properties and values are displayed in the properties view. Now we are considering assigning the default JRE for the Workbench in working with JREs in tasks. Here's how you can change the default JRE. The default JRE is used for compiling and launching Java programs in all projects unless you specifically override the default JRE on a project build path or on a launch configuration. Here's how you can change the default JRE. Step 1, open the Java, then install JRE preference page. Step 2, click the box on the line for the JRE you want to assign as the default JRE in the Workbench. If the JRE you want to assign as the default does not appear in the list, you must add it. Then click OK. Note, change in the default JRE may cause a build to occur if you have a auto build enabled project, then built automatically, or in the general then workspace preference page. Now we are considering Workbench options preferences in debug preferences in PHP preferences. The Workbench options preference page is accessed from the window or preferences or PHP or window preferences, PHP debug, then Workbench options. The Workbench options preference dialog will allows you to configure the default behavior of the workspace during the debugging process. The Workbench options preference page is accessed from window, then preferences, then PHP, then debug, then Workbench options. The Workbench options configuration options are the Workbench options configuration options here allow multiple debug sessions. Select whether to allow multiple debug sessions to run simultaneously, always, never, or prompt. Switch back to the PHP perspective when the debug is terminated. Select whether the PHP perspective will open when the debug is terminated. Always, never, prompt. And Workbench options open in browser. Mark the checkbox for the debugged file to be displayed in a browser during debugging. Open PHP debug views mark the seven checkbox for PHP debug views to be displayed when the debug session is launched. By default, a dialog will appear when a debug session is launched asking whether you want to open the debug perspective when the debugging session is run. To change this behavior, open the perspective preference dialog box by going to window, then preference, then run or debug, then perspectives, and select always, never, or prompt. In the open the associate perspective when launching category. Now we are considering restoring a deleted workbench element in using the local history in tasks. Step 1, ensure that a Java view that show the Java elements inside files such as the outline view is visible. Step 2, open the compilation unit to which you want to add the previously removed data element from the local history. Step 3, activate the editor by clicking its tab in the editor area, and the Java view shows the content of the Java file. Step 4, in the Java view, select the element to whose container type you want to restore the deleted element. Step 5, from the type pop-ups menu in the Java view, select restore from local history. Step 6, in the upper left pane of the resulting dialog, all available editions of the selected element in the local history are displayed. Step 7, in the left pane, check all element that you want to replace. Step 8, for every checked element, select an edition in the right hand pane and view its content in the bottom pane. Step 9, when you have identified the edition you want to restore, press restore. The local history editions are added into the editor. Now we are considering creating web service using Ant tasks in the workbench in creating web services and clients using Apache CXF and Ant task in tasks. To begin, you need to modify the Ant properties file than was imported using the Ant files wizard in the prerequest. You can use Ant through the Eclipse workspace to generate a web service using CFX runtime environment. Both top-down and bottom-up web services development is supported with Ant tasks. Before creating the web service, you must complete the prerequisites in point 2. Next point, if you are creating a top-down web service, create or import a WSDL file into the web content folder of the dynamic web project. Next point, if you are creating a bottom-up web service, create or import Java Bean into the source folder of the dynamic web project. Note there are certain limitations when developing a bottom-up web service using Ant task as opposed to the web services wizards. If an explicit service endpoint interface SCI is requested, one must be extracted beforehand, and both the implementation class and SEI must be annotated with at javax.jws.webservice before running the Ant build file. To begin, you need to modify the Ant properties file than was important using the Ant files wizard in prerequests. Step 1, edit CXF underscore td java.properties if doing top-up, top-down development, or the CXF underscore view java.properties file for bottom-up development. Ensure scenario type parameter is set to service. Set the initial selection parameter to the location of your WSDL file, top-down or Java Bean bottom-up. All other parameters are optional and should be deleted if not explicitly explicitly set. The default values for the remaining properties will be retrieved from the dynamic web project settings and preferences. For additional information on how to set parameters, refer to top-down CFX web service and task properties file reference in the documentation, or bottom-up CFX web service and task properties file reference in the documentation. Save the properties file. Step 2, select the CFX underscore td java xml top down or CFX underscore bu java .xml bottom up, and from the top level menu, and then select run, then external tools, then external tools configuration. Step 3, in the dialog that opens, select and build, and then select new launch configuration button. In the toolbar, select JRE tab, then select run in the same JRE as workspace and click apply, and then click then run. A build successful message will be output to the console once the web service has been generated. Now we are considering creating a web service client using the AND task in the Workbench. In creating web services and client using Apache CF and AND task in tasks, you can use AND through the Eclipse workspace to generate the web service client using CXF runtime environment. Before creating the web service, you must complete the prerequisiting. To begin, you need to modify the AND properties file than was the imported using AND files wizard in the prerequisites. Step 1, edit the CFX underscore client.properties file that you imported in the prerequisite step. Then ensure the scenario type parameter set to client. Then set the initial selection parameter to the location of your WSDL file. All other parameters are optional and should be deleted if not explicitly set. The default values for the remaining parameters will be retrieved from the dynamic web project settings and preferences. For additional information on how to set parameters, you can refer the CFX web service client and task properties file reference in the documentation, and save the properties file. Step 2, select the CFX underscore client.xml file, and from the top level menu, and select run, then external tools, then external tool configuration. In the step 3, in the dialog that opens, select and build, and then select a new launch configuration button. In the toolbar, select JRE tab, then select run in the same JRE as the workspace. Click apply and then run. Step 4, build successful message will be output to the console once the web service has been generated. Now we are considering creating web services using AND task in Workbench. In creating Axis runtime environment web services and client using web services and task in developing web services applications. In order to create the web service, you need to modify the AND file and the service and properties file. You can use AND through the Eclipse workspace to generate a web service using Axis runtime environment. Both top-down and bottom-up web services development is supported with the AND tasks. Before creating the web service, you must complete the prerequisite listed in. And next point, if you are creating a top-down web service, create or import the WSDL file from the web content folder of the dynamic web project you created. The next point, if you are creating a bottom-up web service, create or import the Java Bean into the SRC folder of the dynamic web project. In order to create the web service, you need to modify the AND file and the service and properties file. Step 1, edit the AND file axis underscore tdjava.xml or axis underscore bujava.xml that you imported in the prerequisite steps. Ensure that it points to the service and properties file. It should contain the line stating property file equal axis underscore tdjava.properties or property file equal axis underscore bujava.properties. Save any changes that you have made. Step 2, edit the properties file that you imported in the prerequisite steps. Ensure that the scenario type parameter is set to service. Set the workspace parameter so that it points to the location of your WSDL file or Java bin. All other parameters are optional and should be deleted if not explicitly set. The default values for remaining parameters will be retrieved from the dynamic project settings and preferences. For additional information on how to set these parameters, refers to top-down access web service and task properties file reference, bottom-up access web service and task properties file reference in the documentation. Save the properties file. Step 3, right click access underscore tdjava.xml or access underscore viewjava.xml and select run as, then run build. In the dialog that opens, select JRE tab, then select run in the same JRE as the workspace. Click apply and then click run. Once your web service has been generated, the console displays the build successful message. The WSDL file for the service will have been created and placed in the dynamic web projects web content /WSDL folder. The following files will have been created and placed in the subdirectory of the dynamic web projects web content /web-inf folder: web.xml, undeploy.wsdd, deploy.wsdd. If you are creating top-down web service files similar to the following will be created and placed under the dynamic web projects src folder. Depending on the WSDL file on which the web service is based, the file form for your web service may be different. Service underscore name underscore port type.java, service name service Java, service name servlet locator Java, service name SOAP impl Java, service name SOAP skeleton.java, service name SOAP stub.java. Here the top-down access web service and task properties file reference. The access underscore tdjava.properties file is used to pass the data to the services, data to the web services and tasks when creating an access web service. This file shows the available options. Bottom-up access web service and tasks properties file reference. This access the access underscore bu java.properties file is used to pass the data to the web services and task when creating an access web service. This file shows the available options. We can consider this as an error example. Problems occurred when invoking code from plugin org.eclipse.ui.workbench. If you want to start your Eclipse, choose your Workbench to load and then Eclipse stops. You probably have a Workbench error. To fix this, follow the steps. Go to workspaces, then your workspace, then .metadata, then .plugins. Find the folder org.eclipse.e4.workbench, delete it, restart Eclipse. Now the problem is fixed and Eclipse will start again, but be aware that your workspace layout will be back to default. This error can be found in the file workspaces /your workspace /metadata /log file. Now we are focusing on JFace. JFace is a UI toolkit with classes for handling many common UI programming tasks. JFace is a Windows system independent in both its API and implementation and is designed to work with SWT without hiding it. JFace includes the visual UI toolkit components of image and font registries, text, dialog, preference and wizard frameworks, and progress reporting for long-running operations. Two of its more interesting features are actions and viewers. The action mechanism allows user commands to be defined independently from their exact whereabouts in the UI. Viewers are model-based adapters for certain SWT widgets, simplifying the presentation of application data structured as lists, tables, or trees. Here you can see JFace architecture. JFace establishes a layer between application's business logic and the bare bones SWT widgets. JFace uses methods like setText and setIcon to actually display data in widgets, and registers for low-level event as necessary. It also offers events to the application itself, but these are special in that they translate from the widget level to the model level. For instance, when a user selects a row in table widgets, SWT reports the index of the row. JFace translates that index into the model element, and it has previously rendered in the row and reports that this model element has been selected. In effect, the application is shielded from the cumbersome details and can always work in terms of its own data structures. In effect, of course, it still listens to the events such as button clicks directly on the SWT widgets, and translate this into operations in the model. JFace follows model view separation in getting data to be displayed from the model and listening to the change notification of the model to keep the display up to date. Here you can see SWT interacts with JFace. setText and setIcon are passed from JFace to SWT. Events are passed from SWT to JFace. JFace interacts with model. Get data is passed from JFace to model. Change is passed from model to JFace. And SWT is connected to listeners, and events are passed from SWT to listeners. JFace is connected to listeners. Model and view events are passed from JFace to listeners, and listeners are connected to model, and invoke operations are passed from listeners to model. Here you can see a bit more detailed JFace architecture. We will now discuss the various roles and relationships. Here we focus on viewers and their collaborations. The listeners, which implement the application reactions to user input in the sense of controllers. JFace viewers target specific widget types. The core contribution of JFace layer relates to its selection of generic viewers, each of which targets a specific type of widgets. A table viewer targets tables. A combo viewer targets a combo box, and so on. Viewers use the widget specific methods for displaying data and listen for widget specific events. JFace viewers access the application data through adapters. One question not addressed is how JFace will actually access the application specific data. How is a generic viewer supposed to know the right get data method and the implementation of observer pattern of specific data structures? First, each viewer holds a reference to the model in its property input. However, that input is a generic object, so the viewer never accesses the model itself. Instead, the viewer is parameterized by two adapter objects that enable it to inspect the model just as required. The content provider is responsible for traversing the overall data structure and for splitting it up into elements for displaying purposes. For a table or list, it provides a linear sequence of elements for a tree-like display. It also accesses the child and parent-like links between the elements. Furthermore, content provider must observe the model and notify viewer about any changes that it receives. Label provider is called back for each element delivered by the content provider, usually to obtain concrete strings and icons to represent the element on the screen. A list viewer will request one text icon combination per element. A table viewer or tree viewer will request one combination of each column. The viewer will also observe the label provider to be notified about changes of the text and icons to be displayed. The text-related viewers, text viewer and source viewer, deviate from this schema in that they expect an implementation of iDocument as their model. The document itself then includes a text-specific access operation without requiring a separate adapter. The framework includes a deliberate redundancy regarding changes in the model. When values change within a data element, then those may be translated for the viewer either by the content provider by calling the viewer's update method or by the label provider by firing change events. Each mechanism has its merits. On the one hand, the content provider observes the model anyway, so the label provider can often remain passive. On the other hand, some generic label providers, such as those used in data binding, may wish to avoid relying on a specific content provider. Here you can see widgets interacts with viewer. Set icon and set text are passed from viewer to widgets, and selection is passed from widget to viewer. Viewer interacts with content provider. Get elements are passed from viewer to content provider, and refresh is passed from content provider to viewer. Content provider interacts with model. Get data is passed from content provider to model, and change is passed from model to content provider. Viewer is connected to model, and input is passed from viewer to model. And widget is connected to listeners. Events are passed from widget to listeners. Viewer is connected to listeners. Model level events are passed from viewers to listeners. Viewer is connected to label provider. Get text, get icons are passed from viewer to label provider. Listeners are connected to model, and invoke operations are passed from listeners to model. Now we are considering here you can see wizards. A wizard is composed of several different underlying parts. Wizards are used to guide user through a sequence of tasks. Your plugin can contribute wizards at predefined extension points in the workbench. It can also create and launch its own wizards. When you contribute to a workbench wizard extension point, the actions that launch the wizard are already set up by the workbench. You need only supply the wizard that will be used. If you need to launch other wizards that are not already defined in the workbench wizard extension points, you must launch them yourself. You can launch your own wizards by adding an action to a view, editor, pop-up, or an action set. A wizard is composed of several different underlying parts. Wizard dialog. The wizard dialog is the top level dialog in a wizard. It defines the standard wizard buttons and manages a set of pages that are provided to it. When you contribute to a workbench wizard extension, you do not have to create a wizard dialog. One is created on your behalf by the workbench, and your wizard is set into it. The wizard dialog performs the enabling and disabling of the next, back, and finish buttons based on the information it obtained from the wizards and the current wizard page. Wizard. The wizard controls the overall appearance and behavior of the wizard, such as title bar text, image, and availability of a help button. Wizards often use corresponding dialog settings to obtain and store the default values for the settings of the control on the wizard pages. Wizard class implements many of the details for standard wizard behavior. You typically extend this class to implement behavior specific to your wizard. The primary responsibilities of your wizard will include creating and adding your pages to your wizard, implementing the behavior that should occur when the user presses the finish button. Wizard page, iWizard page define the controls that are used to show the content of the wizard page. It responds to events in its content areas and determines when the page is completed. Your wizard page typically extends the wizard page class. The primary responsibilities of your wizard page will include creating the SWT controls that represent the page, determining when the user has supplied enough information to complete the page, that is, when the user can move to the next page. With regarding important classes and interfaces, here we can consider wizard dialog. The class wizard dialog in package org.eclipse.jface.wizard, a dialog to show a wizard to the end user. In the wizard we can consider iWizard, the interface iWizard in package org.eclipse.jface.wizard. Interface for a wizard. A wizard maintains a list of wizard pages stacks on top of each other in the card layout fashion. We can also consider wizard class wizard, package in the package org.eclipse.jface.wizard, an abstract based implementation of wizard. A typical client subclasses wizard to implement a particular wizard. We can consider interface iWizard page in package org.eclipse.jface.wizard. Interface for a wizard page. We can also consider class wizard page in package org.eclipse.jface.wizard, an abstract based implementation of a wizard page. Here you can see the wizard and back and next and finish and cancels are inside the wizard dialog. Wizard page, the content is inside wizard, the page set. Wizard is connected to page set. Page set consists of a number of wizard pages. Wizard page is connected to wizard page in page set is connected to wizard page here in wizard. Example, we can consider this code. Here you can see a hello world extend application window, and this class has run method and control and create contents method. As an example 2, we can consider setting up an Eclipse project to use SWT and JFace. Step 1. Identify the required external jar files for JFace. Step 2. Create an Eclipse project called org.eclipse.swt that will have all the required SWT and JFace jar files on its build path, and configure the order and export tab of the build path to export these files. This project will supply the required jar files to any other Eclipse project that needs them. Step 3. On any new Java projects that need to use SWT or JFace, simply add the org.eclipse.swt project as a required project on the projects tab of the build path. As an example 3, we are considering package org.eclipse.jface.action. Provides support for shared UI resources such as menus, toolbars, and status lines. Now we are considering JFace dialog wizard in SWT or JFace or RCP in wizards. The wizard generates the following code. The class dialog. A dialog is a a specialized window used for narrow focus communication with the user. This is in the package org.eclipse.jface.dialogs. Subclasses of the JFace dialog class can be created using JFace dialog wizard. The wizard can be selected from the drop down designer wizards menu or from the Eclipse new wizard. To use the wizard, select the project's source folder and package to contain the class. Then enter the class name and hit finish button. This wizard generates the following code. When editing JFace dialogs, any widget may be added to the main content area. In the button bar area, only dialog buttons may be added on the Java viewers palette. Here the class dialog, a dialog is a specialized window used for narrow focus communication with the user. Now we are considering JFace title area dialog wizard. The wizard generates the following code. The class title area dialog, a dialog that has a title area for displaying a title and an image, as well as a common area for displaying a description, a message or an error message. This is in the package org.eclipse.jface.dialogs. Subclass of the JFace title area dialog class can be created using the JFace title area dialog wizard. The wizard can be selected from the top-down drop-down designer wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and package to contain the class. Then enter the class name and hit finish. The wizard generates the following code. When editing JFace title area dialogs, any widget may be added to the main content area. In the button bar area, only dialog buttons may be added on JFace viewers palette. The class title area dialog, a dialog that has a title area for displaying a title and an image, as well as a common area for displaying a description, a message or an error message. Now we are considering JFace application window wizard. The wizard generates the following code, including main method when the toolbar template is selected. The class here subclasses of the JFace the class application window is an high-level main window with built-in support for an optional menu bar with status menus, an optional toolbar, and optional status line. This is in the package org.eclipse.jface.window. Subclass of the JFace application window class can be created using JFace application window wizard. The wizard can be selected from the drop-down designer wizard menu or from the Eclipse new wizard Eclipse new wizard. To use the wizard, select the project source folder and package to contain the class. Then enter the class name and hit the finish button. By default, wizard will generate templates using standard SWT toolbar. Under Eclipse 3.0 and higher, the wizard presents two templates, using toolbar and one with cool bar. The menu the menu bar is composed of menu managers and JFace actions, and the toolbar is composed of toolbar managers and JFace actions. The special JFace actions palette is provided to manage this. Here you can see again the menu bar is composed of menu manager and JFace actions, and the toolbar is composed of toolbar managers. Sorry, this is JFace actions and toolbar managers and JFace actions. The special JFace actions palette is provided to manage this. The wizard will generate the following code, including main method when the toolbar template is selected. The class application window, and application window is a high level main window with built-in support for an optional menu bar, an optional with menu bar with standard menus, an optional toolbar, an optional status line. Now we are considering JFace wizard. The wizard generates the following code. The class wizard, an abstract base class implementation of a wizard. Typical client subclasses wizard to implement the particular wizard. This is in the package org.eclipse.jface.wizard. Subclass of the JFace wizard class can be created using JFace wizard. The wizard can be selected from the drop down wizard menu or from the Eclipse wizard from the Eclipse new wizard. To use the wizard, select the project source folder and the package to contain the class. Then enter the class name. Use the add button to add individual wizard pages. That have already been created, and hit finish button. The wizard will generate the following code. Now we are considering JFace wizard page wizard. The wizard generates the following code. The class wizard page, an abstract based implementation of a wizard page. This is in the package org.eclipse.jface.wizard. A subclass of the JFace wizard page class can be created using the JFace wizard page wizard. The wizard can be selected from the drop down wizard menu or from the Eclipse new wizard. To use the wizard, select project source folder and package to contain the class. Then enter the class name and hit the finish button. The wizard generates the following code. When editing JFace wizard pages, widgets may only be added to the main content area. Now we are considering viewers in JFace UI framework. We first saw a viewer in README tools view contribution inside the README sections view here. The class list viewer, a concrete viewer based on an SWT list control. This is in the package org.eclipse.jface.viewers. Why would you ever want to use a viewer when we have already seen that the Workbench UI contributions like viewers, editors, wizards, and dialogues can be implemented directly with SWT widgets? Viewers allow you to create widgets while still using your model objects. If you use SWT widget directly, you have to convert your objects into the strings and images expected by SWT. Viewers act as an adapters on SWT widgets, handling the common code for handling widget events that you would otherwise have to implement yourself. First we saw a viewer in the README tool view contribution inside the README section view here. Note, viewers can be used to provide the implementation for both Workbench views and editors. The term viewer does not imply that they are only useful for implementing views. For example, text viewer is used in the implementation in many of the Workbench and plugin editors. Now we are considering actions in actions and contributions is deprecated. The code below implements the about action. This is one of the simplest simple actions in the Workbench. The class action, the standard abstract implementation of an action. This is in the package org.eclipse.jface.action. An action, iAction, represent a command that can be triggered by the end user. Actions are typically associated with buttons, menus, menu items, and items in toolbars. Although actions do not place themselves In the UI, they do not have UI oriented properties such as tooltip text, label text, and an image. This allows other classes to construct widgets for the representation of the action. When the user triggers the action in the UI, the action's run method is invoked to do the actual work. A common pattern in the run method is to query the workbench selections and manipulate the objects that are selected. Another common pattern is to launch a wizard or dialog when action is chosen. You should not directly implement the iAction interface. Instead, you should subclass an action class. Browse the subclass of the class to see the menu of the common patterns for actions. Code below implements the about action. It is one of the simple actions in the workbench. You can see the run method here. Now we are considering image descriptors and the registry. Basically, image descriptor in image descriptors and the registry in user interface resources. The following code shows an example for this. The class image descriptor. An image descriptor is an object that knows how to create an SWT image. It does not hold into images or cache them, but rather just create them on demand. An image descriptor is intended to be a lightweight representation of an image that can be manipulated even when no SWT display exists. This is in the package org.eclipse.jface.resources. The image descriptor class can be used as a lightweight description of an image. It specifies everything that is needed to create an image, such as the URL or file name where the image can be obtained. Image descriptors do not allocate an actual platform image unless specifically requested using the create image method. Image descriptors are the best strategy when your code is structured such that it defines all the icons in the place and allocate them as they are needed. Image descriptors can be created at any time without concern for OS resources, making it convenient to you create them all in initialization code. When designing APIs, prefer image descriptors over images whenever possible. Clients of your API only hand image descriptors to your API. Your implementation handles the creation and disposal of images, and clients of your API don't need to care about disposing of images. And good example for this approach is in the wizard class. The following code shows an example of this. Now we are considering model operations in long-running operations. The model context class is provided to run an operation that is modeled from the client's code's perspective. It is used inside the different implementations of iRunnable context. The class model context utility class for supporting model operations. The runnable passed to the run method is executed in a separate thread, depending on the value of the passed fork argument. If the runnable is executed in a separate thread, then the current thread either waits until the new thread ends, or if the current thread is in the UI thread, it polls the SWT event queue and dispatches each event. This in the package eclipse.jfs.operation. The model context class is provided to run an operation that is model from the client code's perspective. It is used inside the different implementations of iRunnable context. If your plugin needs to wait on the completion of a long-running operation before continuing the execution, model context can be used to accomplish this while still keeping the user interface responsive. When you run an operation in a model context, you can choose to fork the operation in a different thread. If the fork is false, the operation will be run in the calling thread. If the fork is true, the operation will be run in the new thread. The calling thread will be blocked, and the UI event loop will be run until the operation terminates. Now we are considering creating a control decoration in control decorations in field assist. A decoration can be created for the control. The class control decoration renders an image decoration near a control. It allows clients to specify an image and a position for the image relative to the control. A control decoration may be assigned a description text, which can optionally be shown when the user hovers over the image. Clients can decorate any kind of controls. This is in the package org.eclipse.jfs.fieldassist. Creating a control decoration is straightforward. Clients simply specify the control to be decorated, and the SWT constants describing the position of the decoration relative to the control. Consider the snippet in which the application creates text control inside one of its dialogues. A decoration can then be created for the control. Once the decoration is created, its image and text can be specified. Clients can use set show only on focus method to specify whether decoration should be shown when the control has focus, or whether it should be shown at all times. To set the set show hover method allows clients to configure whether the description text is shown in a hover when the mouse hovers over the decoration. Create a text field. Specify here the create control decoration for the control. Specify the decoration image and the description. Now we are considering new JFS bindings in JFS data bindings in SWT or JFS in data binding. New bindings are created by selecting viewer and input and clicking the bind button. When creating a binding, content provider and label provider can be label provider may be specified. Now we are considering presenting Java elements in JFace Viewer in JDT UI. If you understand the basic platform mechanism when then putting the Java content and label providers together is quite simple. The interface iJava model represent the root Java element corresponding to the workspace element. Correspond to the workspace. Since there is only one such root element, it's commonly refers to as the Java model element. The Java model element need to be opened before it can be navigated or manipulated. Java model element has no parent. It is the root of the Java element hierarchy. Its children are iJava projects. The JDT UI API provides classes that allows you to present the Java model or parts of it in a standard JFace viewer. This functionality is provided primarily by standard Java element content provider. Translates the Java element hierarchy into a data structure accessible by a tree, table, or a list viewer. Java element label provider provides corresponding images and labels for a standard JFace viewer. Java element labels provides corresponding text labels for Java elements. Contents and label providers for JFace viewers. You can see here. If you understand the basic platform mechanism, then putting the Java content and label providers together is quite simple. The example here uses the Java model, iJava model as the input element for the viewer. The standard Java element content provider also supports iJava project, iPackage fragment root, iPackage fragment, and iFolder as input elements. Provide members of a compilation unit or a class. There are more flags defined in the class Java element label provider. Using the Java model as the viewer's input present Java projects on the first level. Now we are considering JFace data bindings in code generation, in preferences in SWT, in Window Builder Pro, Window Builder. This page used to control the various JFace data bindings. Add initial data bindings invocation to GUI creation method. This preference determines whether the initial data bindings method should be generated into the GUI creation method constructor, create contents, init GUIs method, JB init method, etc. Assign return value of init data bindings method invocation to field. This preference determines whether the data binding context returned by the init data bindings method should be assigned to a field or future access. Don't use deprecated method of beans observables. This preference determines the deprecated methods of beans observables are used. When turned on, the tool will generate Eclipse 3.5 compatible code only. When turned off, the tool will generate the code that will run earlier versions of the Eclipse using code that was deprecated in Eclipse 3.5. Enclosing data binding code in try-catch block. This preference determines whether the data binding code will be generated within a try-catch block. Generate observable code for version 1.3 over properties. This preference determines whether the data binding version 1.3 API will be used for generated observables code. Use viewer support for generating JFace viewer bindings. This preference determines whether viewer support is used for generating JFace viewer bindings. Add init bindings invocation to composite constructor. This preference determines whether the init data bindings method should be generated into the constructor for a composite. Default value for new strategy object. This preference determines the default values used for new update value strategies, update list strategies, and update set strategies. This is the default values for new strategies, and here update value strategy, update list strategy, and update set strategy. Generic init data bindings with access. This preference determines visibility of the visibility access of the init data bindings. Init data bindings method. Preview. This shows the sample. This shows a sample of the generated data binding code given the preference settings. Now we are considering standard dialogues in dialogues and wizards. The message dialog. Message dialog displays a message to the user. You can set the dialog title, image, button text, and message in the constructor for this dialog. The class message dialog, a dialog for showing messages to the user. This is in the package org.eclipse.jface.dialogs. Now we are considering application dialogs. Now we are ready to look at the implementation of this action in the README tools window action delegates. The class dialog. A dialog is a specialized window used for narrow focused communication with the user. This is in the package org.eclipse.jface.dialogs. When a standard dialog is too simple for your plugin, you can build your own dialog using the dialog class. Earlier we for example, we can consider open readme browser action in an action set. This action set is shown in the Workbench toolbar and window, then readme file editor menu. Now we are ready to go look at the implementation of this action in the README tools window action delegates. The window action delegate for the action set uses the current selection in the resource navigator view the .readme file to get the list of sections in the readme file. In this list and the Workbench window shell are passed to the selections dialog. When the user select an action, the selection dialogs is opened. The selection dialog is implemented in the readme tool plugin by subclassing the dialog class in the org.eclipse.jface.dialogs package. The dialog class provides the basic support for building a dialog shell window, creating a common dialog buttons, and launching the dialog. Subclasses are responsible for handling the content of the dialog itself. Create dialog area creates the SWT controls that represent the dialog contents. This is similar to the creating the controls for the view or editor. The selection dialogs creates an SWT list to display the list of sections. It uses JFace Viewer to populate the list. We note that our dialog does not have to create any of the buttons for the dialogs since it is this is done by our superclass. Configure shell is overridden to set the appropriate title for the shell window. OK button pressed is overridden to perform the whatever action is necessary when the user presses the OK button. You can also override the cancel button pressed or button pressed int depending on the design of your dialog. Selection dialog does not implement an OK button pressed method. It inherits the do nothing implementation from dialog. This is not typical. Your dialog usually performs some processing in response to one of the dialog buttons pressed. Dialogs can be simple or as complicated as necessary. When you implement a dialog, most of your dialog code is concerned with creating the SWT controls that represent its content area and handling any events necessary while the dialog is up. Once a button is pressed by the user, the dialog can query the state of the various controls or viewers make up the dialog to determine what to do. Now we are considering dialog settings. The following snippet shows how you could obtain the dialog settings for the readme tool. The interface iDialog settings, an interface to use and an interface to store to a storage mechanism for making dialog settings persistent. The store manages a collection of key value pairs. The keys must be strings and the values can be either strings or array of strings. The convenience API to convert primitive types to strings is provided. This is in the package org.eclipse.jface.dialogs. The org.eclipse.jface dialogs package provide a utility class dialog settings. for storing and retrieving keyed values, you can use this class to save and retrieve primitive data types and strings values that you associate with key names. The settings are loaded and saved using an XML file. The abstract UI plugin provides a support for plugin wide dialog settings stored in an XML file in your plugins directory. If a dialog settings file is not found in your plugins directory, an empty dialog settings will be created for you. When the plugin is shut down, any strings that were added to it will be saved in an XML file and retrieved the next time the plugin is starting up. You can access your dialog settings anywhere in your plugin's code. The following code snippet showed how you could obtain the dialog settings for README tool. Values are stored and retrieved using get and put methods. Get methods are named after the type of the primitive that is being accessed. You can store and retrieve Boolean, long, double, float, int, array, and string values. The following snippet shows how we could get dialog settings to initialize control values in a dialog. The value of the settings can be stored later when the OK button is pressed. Initialize the checkbox according to the dialog settings. Store the value of the generate sections checkbox. Now we are considering wizard dialog in wizards. The wizard dialog is the top level dialog in a wizard. It defines the standard wizard buttons and manages a set of pages that are provided to it. The class wizard dialog, a dialog to show a wizard to the end user. This is in the package org.eclipse.jface.wizard. When you contribute to a Workbench wizard extension, you do not have to create a wizard dialog. One is created for you by one is created on your behalf by the Workbench, and your wizard is set into it. The wizard dialog performs the enabling and disabling of the next, back, and finish buttons based on information it obtains from the wizards and the current wizard page. Now we are considering wizard dialogs. The following code snippet shows how this could be done from some action delegates. This method assumes that we know the Workbench and the selection. The class wizard dialog, a dialog to show a wizard to the end user. This is in the package org.eclipse.jface.wizard. Some examples supplied the wizard for a specified extension point. Another perhaps more common case is that you want to launch your own plugins wizard from the some action that you have defined. Wizards are displayed in the UI by placing them in a containing dialog. This detail is handled for you when you contribute to a wizard extension. When you are launching your own wizard, you must display it yourself by wrapping it in a wizard dialog. For example, the README creation wizard could be launched independently by creating a wizard dialog and associating it with the README creation wizard. The following code snippet shows how this could be done from some action delegates. The method assumes that we know the workbench and the selection. If you need to embed a wizard where you are anywhere else in your plugin's user interface, the interface iWizard container defines the necessary protocol for hosting a wizard. Create the wizard. Create the wizard dialog. Open the wizard dialog. Now we are considering validation and page control in multi-page wizards. This means the page will be validated whenever an event is received from a widget to which the page added a listener. The class wizard new file creation page, standard main page for a wizard that creates a file resource. This is in the package org.eclipse.ui.dialogs. The class wizard new file creation page and create readme1 show a common pattern for implementing page validation. Wizard new file creation page define a common event handler for all SWT events, which validates the page, which means the page will be validated whenever an event is received from the widget to which the page is added to a listener. Once the README creation page creates its own controls, it sets the state of the page using validate page. Using this pattern, a wizard page can put all of its validation code in one method validate page. This method that determines the initial state of the page and recalculate the state anytime it received an event from the widget on its page. Since we added the listener to the checkbox, we will recompute the valid state of the page whenever the checkbox received the selection event. Note that the page's handle event method must call a super to ensure that the inherited page validation behavior occurs in addition to any specific event handling for this page. Create controls, add listeners, and lay out the page. Simple section generation checkboxes. Simple section generation checkboxes. Now we are considering creating a custom filtered items selections dialog. In this example, we will contribute the basic search dialog to illustrate the steps needed to create a custom subclass of filtered items selection dialog. Step 1, create a new plugin project using hello world template. Step 2, create a class extending org.eclipse.ui.dialogs.filtered item selection dialog. Let's name it filtered resources selection dialog example. Step 3, choose a source of the resource that will be used during filtering. In our example, we will generate our own set of random strings as strings. Step 4, now let's implement abstract method from the filtered item selection dialog class. Step 5, add the title of the dialog and set simple implementation of selection history in the dialog. Step 6, change run iAction method from the simple action to. Step 7, change tooltip of the simple action from hello Eclipse world to filtered item selection dialog example. Run Eclipse with created plugin and the resulting dialog will look as follows. Here I omit the example codes. You can see the resulting dialog looks as follows here. As an error example, we can consider this entry org.eclipse.jphase 4/2/2010 0810 10:37:22.148 message. Problems occurred when invoking code from plugin org.eclipse.jphase stack 0 java.lang. Illegal argument exception at org.eclipse.jdt.internal.core.util.scan type signature util.java 2710. This error occurred in Eclipse Java EE IDE for web developers, build ID 2009-09-20-1017. As an SW2 example, now we are focusing on SWT. SWT is an open source widget toolkit for Java designed to provide efficient portable access to the user interface facilities of the operating systems on which it is implemented. The standard widget toolkit provides a common OS independent API for widgets and graphics implemented in a way that allows tight integration with the underlying native Windows system. The entire Eclipse platform UI and the tools that plug into it use SWT for presenting information to the user. Here you can see a demo application on Windows 10. Here you can see communication from Java SWT layer to C native layer, native GTK layer. SWT is a layer between platform UI and the underlying JTK 3 or JTK 4 experimental of the system. It can be launched to use JTK 3 or JTK 4, but cannot use them both at the same time. Communication from Java SWT layer to C native GTK layer occurs through calls defined in os.java. The image here describe this hierarchy better. Here we are considering the Linux environment. Here platform UI is connected to SWT. SWT is connected to os.java. os.java is connected to the SWT underscore JTK3 selection via static calls, and os.java is connected to os.h, and then dynamic calls via flag equal dynamic, and os.h is connected to SWT underscore GTK3 selections. If the SWT underscore GTK3 equals 0, then it's connected to GTK2. If the SWT underscore GTK3 equal 1, it's connected to GTK3. GTK2 and GTK3 are connected to GDK. Now we are considering the widget hierarchy. Widget is the widget is the main widget. Everything else extends widget. The most interesting classes are widget, control, and composite. Most widgets fork off this. As such, it is useful to be aware of fields, methods in parent classes in which methods get overridden by children. In Eclipse, you can control plus click on a method to see its super implementation or derived implementation. This is very useful. The illustration here shows the widget hierarchy. Here widgets interacts with menu, control, scroll bar, item, and tracker. Control interacts with button, label, progress bar, sash, scale, slider, and scrollable. Scrollable interacts with list, composite, and text. Composite interacts with canvas, C combo, cool bar, C tab folder, drill down composite, group, SAS form, scrolled composite, tab folder, table tree, toolbar, tree, view form. Here item interacts with cool item, C tab item, menu item, tab item, table column, table item, table tree item, tool item, and tree item. Here we are considering an incomplete diagram of some widgets and their handles in GTK handles. GTK handles are basically GTK pointers to the widgets. When you first look at a widget, you generally first look at the handles that are defined in the widget. For example, each SWT widget is often made up of several GTK widgets or has pointers to GTK widgets. In general, create handle is good place to start when you first look at a widget. Also inspect asterisk handle asterisk methods of the current widget and the widgets above the hierarchy, parent handle, font handle, child handle, etc. They all contain subtleties which are useful. Handle declarations are inherited, but they are allocated and assigned at a specific widget level. For example, a widget declares handle. Control declares fix handle, but they never allocate them. These will be allocated further down the widget tree. In individual widgets themselves. For example, here is an incomplete diagram of some widgets and their handles. You may observe that the widget has widgets has handle defined. The combo has button handle. Combo has the button handle defined. Here you can see widget and you can see handle here. Control is control inherits widget. You can see fix handle here. Button inherits button and scrollable inherits control. In button you can see box handle, label handle, image handle, arrow handle and group handle. Text and composite inherits scrollable. In text you can see buffer handle. Combo inherits composite. In combo you can see a button handle, entry handle, text renderer, cell handle, pop-up handle and menu handle. Here you can see a flowchart describe the process of adding a new function to os.java very well. Here does the function exist in the in os.java already? If it doesn't exist or no, then it is connected to add method signature to os.java. It is connected to selection do I need to make it dynamic? If it is yes, it's connected to add dynamic flag to method in the os.java, and it is connected to add function signature to os.h, and it is connected to rebuild gtk tools so file. Do I need to make it dynamic? If it is no, then it's connected to rebuild gtk2 os gtk2 so file. It is connected to rebuild gtk3 so file, and it is connected to life is good here, the function. Does the function exist in os.java already? If it is yes, then it's connected to the function. Here life is good. In adding new functions are introduced in JTK3 and old functions are deprecated. In these situations, we need to manually add these method signatures to os.java and os_custom file. Dynamic versus static function. Dynamic functions are not built during compile time. They are only called at runtime. This allows us to have GTK3 functions in GTK4 in a GTK4 built, or run deprecated functions only in GTK3 or some specific GTK strict version range. Dynamic functions have an annotation at method flag equal dynamic. Rebuilding SO files. After you add a new function to os.java and os.h, you need to rebuild the SO file for GTK 3 and GTK4. Dynamics methods and os underscore custom.h. Before adding a new function to os.java, you should understand dynamic functions. If you inspect os.java and look at the Java doc of some of the functions, you will notice the flag like this at method flags equal dynamic. This means the command is not compiled but called dynamically on the fly runtime. This is useful for functions that are specific for certain versions of GTK. For example, some functions were only introduced in GTK 4. As such, these won't compile on the GTK 3 build. Such, you made those dynamic. Similarly, some GTK 3 functions are deprecated in GTK 4, and so that we only use them in GTK 3. Thus, we make them dynamic. Not all functions have to be dynamic. You should only make them dynamic if there is a need for it. That is, in general, you should only make functions dynamic if they have to be dynamic. This is because if error does exist, this postpones them from compile time to runtime. Now we are considering debugging SWT, fixed container, and GTK. To debug the C part of the of a running Java application, you need to attach yourself to the Java virtual machine JVM inside Eclipse. But before doing so, you need to compile GTK and SWT binding with debug flags and optimizations turn off. Here's a diagram to illustrate. Further, since eclipse.platform.swt is a Java project that contains C code, you will have to create a C project that link to that folder to debug the C code. As a note, the source and binaries will be in a different folders. So you will need to create a source and a debug C project. Here you can see Java SWT, and here SWT fixed container and GTK needs to be compiled with debug support and optimizations turn off. SWT fixed container is connected to GTK here. SWT is connected to GTK here. Here JVM C code we attach to a JVM to debug this part. Here you can see SWT widgets. This is these screenshots for many of the widgets included in SWT. SWT widgets are located in packages org.eclipse.swt.widgets and org.eclipse.swt.custom. Widgets extend either the widgets or the control class. Several of these widgets are depicted in this here. The composite class composite class is a container which is capable of containing other widgets. The group class is another container which is able to contain other widgets. Additionally, draws a border around itself and allows you to set a header for the grouped widgets. Here, browser instance of this class implement the browser user interface metaphor. It allows the user to visualize and navigate through HTML documents. Button class button instance of this class represent a selectable user interface object that issues a notification when pressed and released. Here you can see a SWT button with SWT dot arrow, and here SWT dot push. No, here SWT push here, and here SWT dot check, and here SWT dot button with SWT dot radio. Here button SWT dot toggle. Here you can see canvas, class canvas. Instance of this class provide a surface for drawing arbitrary graphics. Combo, the class combo. Instance of this class is control. Instance of this class controls that allow user to choose an item from a list of items, or optionally enter a new value by typing it into an editable text field. Often combos are used in the same place where the single selection list widget could be used, but space is limited. A combo takes less space than a list widget and shows similar information. Composite, the class composite. Instances of this class are controls which are capable of containing other controls. Coolbar, class coolbar. Instance of this class provide an area for dynamically positioning the items they contain. Class ctab folder. Instance of this class implement the notebook user interface metaphor. It allows the user to select a notebook page from the set of pages. Class here datetime. Instance of this class are selectable user interface objects that allows the user to enter and modify the date or time values. Expand bar, class expand bar. Instance of this class support the layout of selectable expand bar items. Group, class group. Instance of this class provide an edge border with an optional title. Label, class label. Instance of this class represent a non-selectable user interface object that displays a string or image. When separator is specified, displays a single vertical line or horizontal line. Link, class link. Instance of this class represent a selectable user interface object that displays text with links. List, class list. Instance of this class represent a selectable user interface object that displays the list of strings and issues notification when a string is selected. A list may be single or multi-select. Menu, class menu. Instance of this class are user interface object that contain menu items, progress bar, class progress bar. Instance of this receiver represent represent an unselectable user interface object that is used to display progress, typically in the form of a bar. Class hash. Instance of this receiver represent a selectable user interface object that allows the user to drag a rubber band outline of hash within the parent control. Scrolled composite. Class scrolled composite. A scroll composite provides the scroll bars and will scroll its content when the user uses the scroll bars. Shell. Class shell. Instance of this class represent the windows which the desktop or window manager is managing. Instances of that do not have a parent, that is, they are built using the constructor which takes a display as the argument, are described as top level shells. Instances that do not have the parent are described as instances that do have a parent are described as secondary or dialog shells. Slider. Class slider. Instance of this class are selectable user interface objects that represent a range of positive numeric values. Scale. Class scale. Instance of this receiver represent a selectable user interface object that represent a range of continuous numeric values. Spinner. The class spinner. Instance of this class are selectable user interface objects that allow the user to enter and modify the numeric values. Styled text. The class styled text. A styled text is an editable user interface object that displays lines of text. The following style attributes can be defined for the text: foreground color, background color, font style, bold italic, regular, underline, strikeout. In addition to the text style attributes, background color of the line may be specified. Tab folder. Class tab folder. Instances of this class implement the notebook user interface metaphor that allows the user to select a notebook page from a set of pages. Table. Class table. Instance of this class implement a selectable user interface object that displays a list of images and strings and issues notification when selected. Text instances of this class are selectable user interface objects that allow the user to enter and modify text. Text controls can be either single or multi-line. When a text control is created with a border, the operating system includes a platform-specific inset around the content of the control. When created without a border, an effect is made to remove the inset that such that the preferred size of the control is the same size as the contents. Here you can see text with the SWT.single, here text with the SWT.multi. Toolbar, the class toolbar, instance of this class support the layout of selectable toolbar items. Tray, class tray of instance of this class represent the system tray that is a part of a taskbar status area on some operating systems. The instance of this class represent the system tray. Tree, class tree, the instance of this class provide a selectable user interface object that displays a hierarchy of items and issues notifications when an item in the hierarchy is selected. Here you can see a few general terms that are used when discussing layout. When writing applications in SWT, you may need to use layouts to give you a window specific look. A layout controls the position and size of children in a composite. Layout classes are subclasses of abstract class layout. SWT provides several standard layout classes. You can write custom layout classes. In SWT, positioning and sizing does not happen automatically. Applications can decide to size and place composites children initially or resize or in a resize listener, or they can specify a layout class to position and size the children. If children are not given a size, they will have zero size, and they will have cannot be seen. The diagram here illustrates a few general terms that are used when discussing layout. The composite, in this case tab folder, has location, client area, and trim. The size of the composite is the size of the client area plus the size of the trim. The composite has two children that are laid outside by the side. Layout is managing the size and position of the children. the layout is managing the size and position of the children. This layout allows spacing between children and margin between children and the edges of the layout. The size of the layout is the same as the size of the composites client area. The preferred size of the widget is the minimum size needed to show its contents. In the case of composite, the preferred size is the smallest rectangle that contains all of its children. If children have been positioned by the application, the composite computes its own preferred size based on the size and position of the children. If a composite using layout class to position its children, it asks the layout to compute the size of its client area and then adds the trim to determine its preferred size. Here you can see composite location here XY and composite client area here XY. Here you can see the composite client area with layout width. Here you can see the composite width. Here you can see the trim, and here you can see the trim. Here you can see the height. Here you can see the composite client area height or layout height, and here you can see composite height. As an example, we can consider this code segment. The following is the basic Hello World program using SWT. It shows a window shell and a label. Contrary to swing, display class is necessary to access underlying operating system, and its resources must be explicitly disposed of when they are no longer used. As an example too, we can consider steps to import SWT library. Right click on Java project, click properties. Step 2, click Java build path, then libraries, then add variable, then configure variable. Step 3, click new, then type a new variable name SWT_lib in names field. Step 4, click file and browse to SWT library file. PS SWT library is located at Eclipse plugin folder. Its name usually formatted as org.eclipse.swin32.win32.x86 _version number.jar. Here you can see the step 2. Click Java build path, then libraries, then add variable, then configure variables. Now we are considering package org.eclipse.swt, SWT constant and error handling support. Now we are considering package org.eclipse.ui.swt, application programming interfaces for interaction with an extension of the Eclipse platform user interface. Now we are considering widgets application structure in widgets. Since the application only displays string hello world, it does not need to register for any widget events. The class label, instances of this class represent a non-selectable user interface object that displays a string or image. When a separator is specified, displays a single vertical or horizontal line. This is in the package org.eclipse.ui.widgets. When you are contributing UI elements using platform Workbench extensions, the mechanics of starting up SWT are handled for you by the Workbench. If you are writing an SWT application from scratch outside the Workbench, you must understand more about SWT's application structure. A typical standalone SWT application has the following structure: create display which represent SWT session, create one or more shells which serve as main windows for the application, create any other widgets that are needed inside the shell, initialize the sizes and other necessary states for the widgets, register listeners for widgets events that needed to be handled, open the shell window, run the event dispatching loop until exit conditions occurs, which is typically when the main shell window is closed by the user. Dispose the display. The following code snippet is adapted from the org.eclipse.sw.examples.helloworld.helloworld2 application. Since the application only displays the string hello world, it does not need to register for any widgets events. The display represents the connection between SWT and the underlying platform's GUI system. Displays are primarily used to manage platform event loop and control communication between the UI thread and other threads. For most applications, you can follow the pattern that is used here. You must create a display before creating any windows, and you must dispose of the display when your shell is closed. You don't need to think about the display much more unless you are designing a multi-threaded application. Shell. A shell is a window managed by OS Platform Window Manager. Top-level shells are those that are created as child of the display. These windows are the windows that users move, resize, minimize and maximize while using application. Secondary shells are those that are created as a child of another cell. These windows are typically used as dialog windows and other transient windows that only exist in the context of another window. Parents and children. All widgets that are not top-level shells must have a parent. Top-level shells do not have a parent, but they created associated with a particular display. You can access the display using getDisplay. All other widgets are created as descendants, direct or indirect, of top-level shells. Composite widgets are widgets that can have children. When you see application window, you can think of as a widget tree and hierarchy that roots is the shell. Depending on the complexity of the application, there may be a single child of shell or several children or nested layers of composite with children. Style bits. Some widgets properties must be set at the time a widget is created and cannot be subsequently changed. For example, a list may be a single or multi-selection and may or may not have scroll bars. These properties called styles and are set of the constructor. All widgets constructors take an int argument that is specified bitwise or of all desired styles. In some cases, a particular style is considered a hint. which means that it may not be available on all platforms, but will be gracefully ignored on platforms that do not support it. The style constants are located in the SWT class as public static fields. A list of applicable constants for each widget class is contained in the API reference for SWT. Resource disposal. Platform underneath SWT require explicit allocation of freeing of OS resources. In keeping with SWT design philosophy of reflecting the platform application structure in widget toolkit, SWT requires that you explicitly free any OS resources that you have allocated. In SWT, the widget dispose method is used to free resources allocated with the particular toolkit object. The rule of thumb is that if you create the object, you must dispose it. Here are some specific ground rules for further explain the philosophy. If you create a graphic object or widget using a constructor, you must explicitly dispose of it when you are finishing and using it. When a composite is disposed, the composite and all of its child widgets are recursively disposed. In this case, you don't need the disposed of widgets themselves. However, you must free any graphic resource allocated in conjunction with the widgets. If you get any graphic object or widget without using a constructor, for example, control.getBackground, do not dispose of it since you did not allocate it. If you pass a reference to your widget or graphics object to another object, you must take care not to dispose all of it while it is still being used. If you create a graphic object for use during the lifetime of one of your widgets, you must dispose of the graphics object when the widget is disposed. This can be done by registering a dispose listener for your widget and freeing the graphics object when the dispose event is received. There's one exception to these rules. Simple data objects such as rectangle and point do not use operating system's resources. They do not have dispose method, and you do not need to have to free them. If in doubt, check the Java doc for the particular class. Now we are considering events. This simple example is adapted from the org.eclipse.swt.example.helloworld.helloworld3. The class control adapter. This adapter class provides the default implementation for the methods described by the control listener interface. This is in the package org.eclipse.swt.events. Once we create a display and some widgets and start up the application's message loop, where does the real work happens? It happens every time an event is read from the queue and dispatched to the widget. Most of the application logic is implemented as a response to the user event. Basic pattern is that you add the listener to some widget that you have created, and when the appropriate event occurs, the listener will be executed. This simple example is adapted from org.eclipse.swt.examples.helloworld.helloworld3. For each type of listener, there is an interface that defines the listener XYS listener, a class that provides the event information XYZ event, and an API method to add the listener. This API method is called 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 the listener. This API method is call add XYZ listener. If there is more than one method defined in the listener interface, then there is an adapter, XYZ adapter, that implements the listener interface and provides the empty methods. All of the events listeners and adapters are defined in the package org.eclipse.swd.events. Now we are considering layouts. The next snippet uses a layout to achieve the same effect. Class fill layout. Fill layout is the simplest layout class. It lays out controls in a single row or column, forcing them to be the same size. This is in the package org.eclipse.swd.layout. Often the best way to handle simple widget positioning is in the resize event listener. However, there are common patterns used by applications when placing widgets. These patterns can be structured as configurable layout algorithms that can be reused by many different applications. SWT defines layouts that provide general purpose positioning and sizing of a child widgets in composite. Layouts are subclasses of the abstract class layout. The SWT standard widgets can be found in the org.eclipse. Layout. There are some general definitions used when resizing and positioning widgets. The location of a widget is its XY coordinates location within its parent widgets. Preferred size of a widget is the minimum size that needed to show its contents. This is computed differently for each kind of widgets. The client area is the area which the child can be placed without being clipped. Trim is the distance between the widget's client area and its actual border. Trim is occupied by the widget's borders or extra space at its edge. The size of appearance of a trim is widget and platform dependent. These concepts are relevant for application regardless of whether a layout is used. You can think of a layout as a convenient way to package resize functionality for reuse. Some additional concepts are introduced by layouts. Some layouts support spacing between widgets in the layout. Some layouts supports margin between edge of the layout and widget displacement widget adjacent to the edge. The following code snippet shows the simple case of an application using resize callback to the size of a label to size of its parent shell. Next snippet here uses the layout to achieve the same effect. Even for this simple example, using a layout reduces the application code. For more complex layout, the simplification is much greater. Here, the class fill layout. Fill layout is simplest layout class. It lays out control in a single row or column, forcing them to be the same size. This is in the package org.eclipse.swd.layout. Now we are considering SWT UI thread in threading issues. The main thread including the event loop for an SWT application has the following structure. The class display, the instances of this class are responsible for managing the connection between SWT and the underlying operating system. Their most important function is to implement the SWT event loop terms of the platform event model. They also provide various methods to accessing information about the operating system and have overall control over the operating system resources which SWT allocates. This is in the package org.eclipse.swt.widgets. The SWT follows the threading model supported directly by the platform. The application program runs the event loop in its main thread and dispatches the event directly to this thread. UI thread is the thread in which the display was created. All other widgets must be created in the UI thread. Since all event code is triggered from the application's UI thread, application code that handles events can freely access the widgets and make the graphics calls without any special techniques. However, the application is responsible for forking the computational threads when performing long operations in response to an event. Note, the SWT will trigger SWT exception for any calls made from non-UI thread that must made from the UI thread. The main thread including the event loop for SWT application has the following structure. Once the widgets are created, the shell is opened and the application reads and dispatches the event from the OS queue. Until shell window is disposed. If there are no events available for us in the queue, we tell the display to sleep to give other application a chance to run. SWT provides special access method for calling widgets and graphics code from the background thread. Start the event loop. We stop when the user has done something to dispose our window. Now we are considering SWT exception in error handling. SWT exception is thrown when a recoverable error occurs internally in SWT. The error code and the message text provide the further description of the problem. The class SWT exception. This runtime exception is thrown whenever a recoverable error occurs internally in SWT. The message text and error code provide the further description of the problem. The exception has a throwable field which holds the underlying exception that caused the problem. If this information is available, that is, it may be null. This is in the package org.eclipse.swt. SWT exception is thrown when a recoverable error occurs internally in SWT. The error code and message text provide the further description of the problem. SWT remains a known stable state after throwing the exception. For example, this exception is thrown when the SWT call is made from a non-UI thread. Now we are considering painting in graphics object life cycle. In graphics, the color red was previously allocated when creating the widget, so it can be used here. The class GC. The class GC is where all drawing capabilities that are supported by the SWT are located instances are used to draw on either an image, a control, or directly on the display. This is in the package org.eclipse.swt.graphics. Once you have allocated your graphics object, you are ready to paint. You should always do your painting inside the paint listener. There are rare cases, particularly when implementing custom widgets, when you paint while responding to some other events. However, this is generally discouraged. If you think you need to paint while handling some other event, you should first try to use redraw method, which will generate another paint event in the OS. Drawing outside of the paint method defeats the platform optimizations and cause bugs depending upon the number of pending paints in the event queue. When you receive a paint event, you will be supplied with the GC pre-configured for drawing the widgets. Do not free this GC. You did not create it. Any other graphics object must be allocated while handling the event or beforehand. Below is a snippet on the org.eclipse. swt.examples.helloworld5 example. The color red was previously allocated when creating the widget, so it can be used here. Here you can see hello world in SWT examples. Now we are considering SWT application wizard. This wizard generates the following code, including main. SWT application window SWT application window wizard creates a main class that instantiates and shows the top level shell. The wizard can be selected from the drop down menu or from the Eclipse new wizard. To use the wizard, select the project source folder and the package that contain the class, and enter the class name to and hit the finish button. The wizard generates the following code, including main method. When editing SWT applications in Windows, all of the SWT layouts, all of the standard SWT layouts, containers and widgets and menus are available. Custom or third-party controls may be added via the choose component command. Now we are considering SWT composite wizard. The wizard generates the following code. Subclass of the SWT composite class can be created using SWT composite wizard. The wizard can be selected from the drop-down wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and package that contain the class, and enter the class name. Then hit the finish button. The org.eclipse.swt.widgets.composite class is the default superclass. You can select org.eclipse.swt.widgets.group as the superclass if you prefer. The wizard generates the following code. When editing SWT composites, all the standard SWT layouts, containers, widgets, and menus are available. Custom or third-party controls may be added via the choose component command. Disable the check that prevents subclassing of SWT components. Now we are considering SWT dialog wizard. The wizard generates the following code, including open method. Subclass of the SWT dialog class can be created using SWT dialog wizard. The wizard can be selected from the drop-down wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and the package that contain the class. Enter the class name and hit the finish button. the org.eclipse.swt.widgets.dialog class is the default superclass. The wizard generates the following code, including the including an open method. When editing dialogues, all the standard SWT layouts containers and widgets and menus are available. Custom or third-party controls may be added via the choose component command. SWT shell wizard. The wizard generates the following code, including the main method. Subclass of the SWT shell class can be created using the SWT shell wizard. Wizard can be selected from the drop-down wizard menu or from the Eclipse new wizard. To use the wizard, select the project source folder and the package containing the class. Enter the class name and hit the finish button. org.eclipse.swt.widgets.shell class is the default superclass. The wizard generates the following code, including the main method. When editing SWT shells, all of the standard SWT layouts, containers, widgets, and menus are available. Custom or third-party controls may be added via the choose component command. Disable the check that prevents subclassing of SWT components. Now we are considering object SWT fields in RIP web client API reference. Here is static SWT.alt. Keyboard or mouse event mask indicating that the alt keys was pushed on the keyboard when the event is generated. This is in the object SWT. This object defines the public constants used by RWT scripting, specifically event types and key codes. Now we are considering event code generation in event handlers. In code generation in preferences in SWT, this preference determines how event handlers are generated. First option, create anonymous class. generates anonymous adapter class located in line with the widget definition. Second option is create inner class, generates an adapter class as an inner class. Options are provided to add inner class at the beginning or end of the class, as well as specify the pattern used to name the inner class. The pattern can include the template variables names enclosed between $ open curly brace and close curly brace shown here. Capitalizing the name of any variable will cause the value of the variable to be capitalized before it is inserted into the resulting text. The pattern can include component name, the name of the component to which the handler is being attached, component class name, the name of the class of the component to which handler is being attached, listener name, it's not there, the name of the event being handled, listener class name, name of the event listener, third option is implement the listener interface in parent class, adds the listener interface to the parent class and adds the appropriate method to the class definition. Here you can see the example. Here you can see Forms API. This page is used to control SWT Forms API options. Generate paint border for method for new composites. This preference control whether a call to paint border for method is generated for each added composite. When borders are turned on for a composite, various widgets are automatically drawn with the flat border. When borders are turned off, widgets are drawn without borders. Automatically adapt method new non-form controls. This preference whether new form controls are automatically adapted using the form toolkit. Now we are considering absolute in layouts in SWT in preferences. This page is used to control the various SWT, then layouts, then absolute options. Use free component placement style. This preference determines whether free mode is used for aligning widgets. Free modes uses widget snapping similar to that used for group layouts. Component gaps. This preference determines the default gaps are used between components and their containers in free mode. Container gaps. This preference determines what default gaps are used between components and their containers in free mode. Apply grid creation flow. This preference determines whether the creation order of the widgets will be adjusted to reflect their position in left to right or top to bottom grid flow. This will affect the default tab border. Use grid snapping. This preference determines whether grid mode is used for aligning widgets. Grid mode uses use a customized snapping grid. Grid step. This preference determines the grid step used in the grid mode. Display grid. This preference determines whether the grid is displayed in grid mode. Display locations and size hints. This preference determines whether location and size hints are shown when moving or sizing widgets. Automatically resize component on text or image property change. This preference determines whether a widget is automatically auto-sized anytime its text or image property is changed. Now we are considering preference page. This page is used to control various SWT preference page options. Editor use same code generation settings as control. This preference determines whether new field editors use the same code generation settings as new controls. Now we are considering new SWT bindings in SWT data bindings. When creating a binding, the update strategy from target to model and model to target may be specified. As well as any strategy specific properties validators and converters. New bindings are created by selecting target, a target property, a source or source property, and clicking the bind button. When creating binding, the update strategy from target to model and model to target may be specified, as well as any strategy specific properties, validators and converters. When the target or model is a text widget and text property is selected, the triggering event may be specified as SWT dot modify, SWT dot focus out, or SWT dot none. Predefined update strategies. Predefined update value strategies: policy underscore update, policy underscore never, policy on request, and policy convert may be selected, or a custom strategy class may be chosen. Now we are considering main features of absolute layout. Selects absolute layout from the layout panel, layout palette, and drop it on the window or composite. Absolute layout or null layout is a simple XY oriented layout. During layout, the live component is shown moving with the tooltip showing its current location or size. Dynamic snap or alignment points are provided to make the convenient to align the composite with other component or the window margin. Resizing a component also snaps to the preferred size of the resized component or to the size vertical or horizontal of any other component on the same parent. Graphical feedback is provided for all widgets size and position operations. Now we are considering main features in SWT fill layouts. Select fill layout from the layouts palette and drop it on the window or composite. Fill layout is the simplest layout class. It lays out controls in a single row or column, forcing them to be the same size. Initially, the controls will be as tall as the tallest control and as wide as the widest. Fill layout does not wrap, but you can specify margins and spacing. You might use the two layout buttons in this taskbar or in a taskbar or toolbar, or to stack checkboxes in a group. Fill layout can also be used when a composite only has one child. For example, if a shell has a group child, fill layout will cause the group to completely fill the shell if margins are 0. Graphical feedback is provided for all drops and move interactions. The spacing can be specified using property pane. Now we are considering main features in form layout. Select form layout from the layouts palette and drop it on window or composite. A form layout class that implements an constraint based layout manager. With constraint based layout, you have independent control over sizing and over the sizing behavior of each of the 4 sides of the widget. The top, bottom, left and right sides can be independently attached to the sides of the parent container or sides of any sibling widget within the same container using either fixed or relative offsets. This proves to be surprisingly powerful and can be used to emulate almost any of the other layout managers. The form layout class is very simple and only specifies the margins of the container. The real power is in the form data object, which holds up our 4 element form constraint objects. The graphical feedback is provided for all widget size and position operations. Support for automatic placement mode and classic mode. Now we are considering main features in grid layout. Select grid layout from the layout palette and drop it into a window or composite. Grid layouts lays out the control children of a composite in a grid. The grid layout has a number of configuration fields. And the controls it lays out can have the associated layout data object called grid data. The power of grid layout lies in ability to configure grid data for each control in the layout. Num columns field is the most important field in the grid layout. Widgets are laid out in columns from left to right, and a new row is created when the number of columns num columns plus 1 controls added to the composite. Graphical feedback is provided for all column, row, and cell interactions. Column and row properties may be changed via a pop-up menu, and convert existing layout from layouts null from form layout etc. to grid layout with intelligent column and row creation. Now we are considering main features in SWT group layout. Select group layout from the layouts palette and drop it on a shell or composite. Group layout is a layout manager hierarchically groups components in order to the position them in a container. Group layout is intended to use by builders but may be hand coded as well. Grouping is done by instances of the group class. Group layout is intended for use by builders but may be hand coded as well. Grouping is done by the instances of the group class. Group layout supports two types of groups: sequential groups and sequential group positions its child elements sequentially and one after another. The parallel groups aligns its child element in one of 4 ways. Each group may contains a number of elements where an element is a group component or gap. A gap can be thought of as an invisible component with a minimum minimum and preferred and maximum size. In addition to group layout supports the preferred gap whose values come from layout style. Elements are similar to a spring. Each element has a range and as specified by the minimum, maximum and preferred size. Gaps have either developer specific range or a range determined by layout style. The range for components is determined from the components get minimize size, get preferred size and get maximum size methods. In addition, when adding components you may specify a particular range to use instead of that from the component. The range for a group is determined by the type of group. The parallel group's range is maximum of the ranges of its element. The sequential group's range is sum of the ranges from its elements. Group layout treats text each axis independently. That is there is a group representing a horizontal axis and the group representing vertical axis. The horizontal group is responsible for determining the minimum preferred and maximum size along the horizontal axis, as well as the setting the x and width of the component contained in it. Vertical group is responsible for determining the minimum preferred and components contained in it. Each component must exist in both a horizontal and vertical group, otherwise an illegal state exception is thrown during layout or when the minimum preferred or maximum size is requested. Graphical feedbacks is provided for all widget size and position operations. Now we are considering main features in SWT row layout. Select row layout from the layout palette and drop it on a window or composite. Row layout determines the size and position of children of a composite by placing them either horizontal rows or vertical columns with the parent's composite. Row layout aligns its control in one row if the type is set to horizontal, and one column if the type is set to vertical. It has the ability to wrap and provide configurable margins and spacings. Row layout has a number of configurable fields. In addition, height and width of each control the row layout can be specified by setting the row data object into the control using set layout data. The graphical feedback is provided for all drop and move interactions. Spacing can be specified by property pane. Now we are considering main features in stack row layout. The select row layout now we are considering main features in SWT stack layout. Select stack layout from the layouts palette and drop it on the window or composites. Stack layout object is a layout manager for container. It treats each component in the container as a card. Only one card is visible at a time, and the container acts as a stack of cards. First component is added to the stack layout object is the visible component when the container is first displayed. The ordering of card is determined by the container's own internal ordering of its components objects. Stack layout defines a set of methods that allow the application to flip through these cards sequentially or to show the specific card. When adding a new widget, the current drop point is highlighted in green. Switch between cards use the using the up down arrows in the upper right corner. Now we are considering main features in swing border layout. Select border layout from the layout palettes and drop it on a window or composite. Border layout lays out the container, arranging and resizing its component to fit 5 regions: north, south, east, west, and center. Each region may contain no more than one component and is defined by the corresponding constant north, south, east, west, and center. When adding component to the container with the border layout, use one of these 5 constants as convenient. Uh, uh, yep, and as convenient, border layout interprets the absence of a string specification, same as the constant center. Graphical feedback is provided for all drop and move interactions. Horizontal and horizontal and vertical gaps can be specified by using the property pane. Now we are considering main features in swing box layout. Select box layout from the layouts palette and drop it to on the window composite. Box layout box allows multiple components to be laid out either vertically or horizontally. Components will not wrap. So, for example, vertical alignment of component will stay vertically arranged when the frame is resized. Nesting multiple panels with different combinations of horizontal and vertical gives an effect similar to grid back layout without complexity. Box layout manage is constructed with an axis parameter that specifies the type of the layout that will be done. For all directions, components are arranged in the same order as they were added to the container. Box layouts attempts to arrange the components at their preference width for horizontal layout or heights for vertical layout. For horizontal layout, if not all the components are in the same height, box layout attempt to make the components as the highest component. If that is not possible, for a particular component, the box layout aligns the component vertically according to the component's Y alignment. Of 0.5, which means that the vertical center of the component should have the same y coordinate as the vertical centers of the other component with 0.5 alignment. Similar for a vertical layout. Box layout attempts to make all components in the column as wide as the widest component. If that fails, aligns them horizontally according to their x alignments. Graphical feedbacks is provided for all drop and move interactions. Graphically show area occupied by struts and springs. Now we are considering compatibility to SWT in differences between RWT and SWT in RAP widgets toolkit. Here you can see the example. RAP generally follows the rule if it compiles, it works. That means that all SWT API implemented in RWT is working within the requirements set by SWT. If an SWT feature is not implemented, the corresponding API is also missing. If this is the case, it is likely because it's hard or impossible to implement in RWT. In some cases, SWT classes and methods are implemented as empty stubs to enable single single sourcing, but only where this is valid according to SWT documentation of AP. Examples are accessing API and some SWT constants that are marked as hint. SWT has developed for desktop application, but RWT is used to build a web application. For this reason, there are some features that SWT supports that RWT does not, while RWT adds some features that are tailored to the specific requirement of web application development. However, RWT does not add any new API to the classes adapted from SWT. All RWT specific features are accessible by API in the namespace org.eclipse.rap.rwt. Many are activated using widgets setData method with the constant from RWT class as the key example here. Other additional features may be accessed via client services. Now we are considering local variable mod in variable generation in SWT, code generation in bidirectional code generation in features in window builder. In local variable generation style, each component is assigned to the unique local variable and initialized at the point of declaration. An option is provided to declare each variable as final. Note that component types marked as final on the variable, then type specific reference page will always be assigned to fields. As an error example, we can consider this. An SWT error has occurred. You are recommended to exit the workbench. Subsequent error may happen and may terminate the workbench without warning. See the .log file for more details. Exception stack trace org.eclipse.swt.swt error. No more handles at org.eclipse.swt.swt.error. swt.java 4517 at etc. Now this is the end of my presentation. Thank you very much for watching it.